Okay, good morning, everyone. This is Greg Volk, and today is September 28th. And today, I apologize, I didn't even put in a write-up for my packing structures talk, but I'm actually going to talk about more things than just that way. It turns out what I was planning to do was present some of the things. I've presented this now for the last 2 years. 3 years at the NPA conference, and so it's not all that new, that stuff. But I did want to talk about some other things that are newer as well. So but I was actually horrified to find out that I left all my models with Terry Wolf in Albuquerque, and he's got my suitcase full of models. So I can't make the usual presentation I make on the packing structures anyway, and so that's why I decided, well, I'm just going to show some of the ideas I've been working on in Mathematica, and I'm not going to necessarily show you all the stuff that's right. It's not a finished thing. This is what I want to do is show you all my work in progress and show you all the difficulties I've been having, and hopefully inspire some of you who are mathematically inclined to help me. Because I think these are important questions to answer. They're not just fun and interesting mathematical things, but might actually have some application. That's what I want to try to convince at least some of you of, and maybe join me in some of these efforts. So that's my motivation. So I changed the title of the talk to be something broader than packing structures, because that's one of many things that I'll be talking about. And so I just called it Neat Stuff I've been working on lately. And I'm asking everyone who's joined since I just started the recording to monitor yourself, mute your microphone so that we don't get feedback and things like that, and then unmute yourself when you're ready. If you want to jump in and say something, I don't mind. But
We should look to see if they're here.
I think they'll knock or ring the bell.
As many of you know, the way I got started in this whole stuff, this whole area of what I might call independent science, was through common sense science, their models of the electron and proton, and I spent a lot of time. I read all their papers. This is back in 2007, and got fascinated with the idea. And basically, the idea is that we're looking for a structure that is self-sustaining, in which matter is held together by its own internal motion, and the motion is actually creating the pinch, if you will, the Amperian pinch that holds it together, and makes the particle stable. So David Bergman, who's the main guy who's been working on this stuff for 20 years now, uses inductance and capacitance. He calculates the inductance and capacitance of a given structure, and then from there he finds the variables, either the size or whatever the variables he's working with, and then using variational principles, he finds the state with respect to that variable that has the lowest potential energy, and he says, well, that's by definition that's what stable means. So, and another way to think of it is if you have an energy well. If the particle is stable when it's at the bottom of the well. So in other words, it's not going to go anywhere. If it's sitting on the side of the hill, it's going to roll down the hill. So it's going to roll to that state and eventually run out of energy if there's friction or whatever, and it's going to sit at the bottom of the hill. And that's the point of stability. And that's basically the idea. So as an example, and this is I'll go ahead and skip ahead to several slides here. One of the things that I got fascinated with early on, this is back in 2007, was Bergman's model of the electron and proton. Now, it doesn't look like much, but basically this is just two rings that he thought of the electron as being a ring that's negatively charged and a proton as being a ring that's positively charged. And these rings are circulating, but they're not rigid. They're able to move around. Okay, and what he was claiming, and this was just fascinating to me, was that the electron, which is much larger, again because it has lower energy but higher. They both have the same angular momentum, so it has a lower frequency, lower energy, because the charge around this circuit is moving at the same speed, c, as the one of the proton. So the proton is actually smaller. The proton is like the figure skater that pulls herself in and spins really fast, and the electron is like a big old Ferris wheel spinning around. But but by virtue of their charge, which is a whole other issue, they're attracted to each other, and they're attracted to each other. The electron is pulled in, the proton is pulled out. They're more or less in this model in the same plane, and they reach a point of equilibrium. And I've actually done the calculations on this, and the fascinating thing is that Bergman was able to derive the anomalous magnetic moment of the neutron, which is about 5 times the magnetic moment of the proton. And that is extremely encouraging to me and to David. And he never did publish this. This was done, my goodness, well, five years ago or so when he was working on this, and it didn't ever get published. Although I consider it just an amazingly important discovery that we're able to create a model that describes this this idea of a neutron. He did publish a paper in 2001 called Notions of a Neutron, but that was kind of only the beginning of this idea. By 2007, he'd made quite a bit of progress. Well, there's pluses and minuses to every model, and this model, the minus is that it doesn't tell us why the electron is negative and the proton is positive. It just assumes that. And that was the question that started to drive me crazy. How can are there two different kinds of things, or is there just one kind of thing that moves in a couple of different kinds of ways? And so that was my motivation even back in 2007, is how does an electron really differ from a proton, and why are they attracted to each other in terms of that? So I've been really driven by that for quite a long time, just to give you a perspective on that. And anyway, another question that's not being addressed in this model is essentially these two circuits. And I should probably get my little pointer here. The outer circuit are treated as lines. He's not really taking into account in this model the thickness around the cross section. He's saying it's extremely thin, so they're very, very thin circuits. But and he gives his mathematics to explain why that is, and it makes sense. But there's a lot of issues with that still aren't resolved. What is the structure across the cross section? That was the thing that really started to bother me. Another thing that I got out of this model way back in 2007 was the idea that where is the energy contained in this model? Well, in other words, going back to Michael Faraday, the matter takes up a relatively small amount of volume, especially if these rings, are extremely thin. So where the matter is very localized, if you will, very small region of space. But where the energy is located that's associated with that matter is spread out through space, because obviously these particles, which are not touching, are nonetheless influencing each other. And that's the whole idea of inductance. And how do we account for that? Well, we have to account for it with some mechanism that takes place throughout space. And that's why we need to, in my mind, create the idea of fields, create the idea even of energy itself, which is the interaction of fields. And I've shown this mathematics in some of my other talks. I don't want to dwell on that at a great deal of time, but that's my thinking. So I'm, in my mind, things like fields, things like energy, things like ether are those things are not matter itself, but they're absolutely necessary mathematically to explain the interactions between matter. And so, whoops, somebody's echoing back. I just heard my voice. I'm not hearing it again, so it's okay. All right, so there's my thinking on this, and I get a lot of that. The other thing that I get out of this is that if you look at the energy of the electron separately, you get you get a certain number. In other words, you calculate the fields of the electron, and then you add up, you square them, adding them up, and you get an energy density, which is, again, throughout space, and I call that the ether if you want. Then you integrate, you add up all those contributions, and you get the total energy for the electron by itself. Then you do the same for the proton by itself, and you get a number. Well, when you add up those two numbers, you do not get the energy, which is proportional to the mass of the neutron. There is something else, and it might be called the mutual energy. And so David Bergman looked at it in terms of mutual inductance. There's the inductance of the electron, there's the inductance of the proton, and then there's this mutual inductance, which is actually taken away. So the sum of the two energies is greater than the energy of the neutron as a whole. There's a negative contribution to energy, which is due to the coupling. And so that fascinated me. What I did was I said, all right, well, let's attribute some of this mutual energy to the electron and some of this mutual energy to the proton, so that each particle separately has an energy that it would have had by itself and the energy that it actually has by virtue of its environment. Hope that makes some sense. This is, again, way back in 2007, I had these ideas, and I wrote an 80-page paper that I've never shared with anybody. It's called Theory of Entropy. I said the ratio of those two energies is the entropy of that particle. That was just my working hypothesis. And I said, well, let's just suppose that's the case. Well, then, in other words, then I could extend that and say the entropy of the whole system is the energy of the individual particles taken separately divided by the other way around. The energy of the whole system divided by the energy of the individual particles taken separately. I said, what if that's the entropy of this system? What if we can do that? And I played with that, and lo and behold, I was able to derive the known laws of thermodynamics from that. And I was able to define, things like enthalpy and temperature and some of these things that aren't understood in terms of this idea. And I thought, maybe I must be onto something here. And it all started from studying this model here and just asking the question, there's energy involved that's not really attributable to one or the other. What if I were to attribute it to one or the other separately? So another way to think of it is, how do we even know something's moving? We know something is moving by virtue of everything else that it moves with respect to. So it has energy in and of itself by virtue of its own internal motions, but it also has energy by virtue of its motion with respect to other things. And in a sense, that is its entropy. Well, it turns out then that things like Einstein's gamma function, in other words, E equals gamma mc squared. The mc squared is the energy that the thing has by virtue of itself. The gamma is the energy that it has by virtue of how it's moving with respect to everything else. So in other words, gamma turns out to be a measure of entropy. It's telling us it's giving us a ratio of the energy of the thing by itself to the energy that it actually has by virtue of being in its environment. I hope everybody's kind of getting all this background, because this is really fundamental to where I'm coming at with entropy. So everything can be understood in terms of that. But the problem is gamma is not enough. Gamma doesn't tell us something else that we need to know about how the particle behaves with respect to its environment. It's only talking about how it's translating with respect to its environment. So gamma mc squared, gamma will always be greater than 1, because an object cannot translate more than not at all. Okay, v squared is going to be a positive number, and it's going to be and the gamma factor will always be greater than 1. Is it possible that an object could have less energy than it would have had? That is, an object in context of its environment could have less energy than it would have in isolation? And the answer is yes, it could. And not by virtue of translation, but by virtue of rotation. And that's exactly what we're seeing in this model. I hope I'm not moving too fast, but this is a really key point. So in other words, there's so many different ways to think of this, and so this is what I've been spending all my time thinking about, is different ways to think of the same problem, constantly coming back to this thing. Is the proton, in a sense, is is borrowing some of its energy from the electron. It's being like carried along like an ether, if you will, with the electron, and so it actually has less energy than it would have had if the electron weren't there. Okay, so the whole is less than the sum of the parts, and that's by virtue of this inductance, this mutual sharing of energy, and only through motion can we get this. Okay, and so motion is the key, and the other point is that there is another factor, and I've called it delta. I don't know, I didn't have another thing to call it, but I call it delta. So in other words, E does not equal gamma mc squared. E equals gamma times delta times mc squared. There's another factor in there. The gamma only accounts for the translational component. The delta accounts for the rotational component, and delta can be less than 1. And so in my paper, which again I wrote this back in 2007, it says that if the rotational energy is strong enough, if there's enough coupling, enough borrowing of energy from its surroundings, and the temperature is low enough. Temperature is basically a measure of relative translation. So temperature is telling us how these billiard balls, these little dots, are moving around in a system relative to each other. Okay, if the temperature is low enough and if the rotational borrowing, if you will, is high enough, then it's possible that the total energy of an actual particle can be less than the sum of its parts. And I said that is the condition for superconductivity. And it's going to be different for different materials, which is why the point at which superconductivity occurs is always above absolute zero. The temperature doesn't have to be zero. It just has to be low enough so that the coupling energy becomes significant enough that it can overcome the case, if you will, of what's going on with the coupling energy. So again, if the whole is less than the sum of its parts, if the energy that's borrowed, in a sense, that's a condition for stability. That's a condition for it's happy to stay there, because it takes more energy, more thermal energy, to pull these things apart than it does for it to just stay there. And so there we go. So the neutron in this model is more or less stable. Now there are conditions. Obviously, the neutron has a 15-minute half-life. Somebody's moving some stuff around. Could you please mute yourselves, everybody? I don't know who that is, but just letting you know. So that's kind of, again, a lot of background on where I'm coming from and how I think of entropy. I think of entropy not as something that is given to us, but something that is derived from the way particles are moving with respect to each other. That's my idea of entropy. So in my mind, entropy is always the whole to the sum of the parts. Okay, and so we say, entropy always increases, and that's, I believe, is due to the fact that we're always thinking in terms of billiard balls moving around as dots, and velocity squared can never be less than 1, or never be less than 0. But on the other hand, when we're talking about rotation, we're talking about things moving in systems like this. That's no longer the case, and we do leave the door open for violations, if you will, of the second law. That's pretty interesting as well. All right, so that's some background. Let me go back to now how that all fits in with some of the stuff I want to talk about today. And so I'm constantly going back to the Bergman model. I've been asking myself now for 5 years, what is a particle? Let me go back to the Bergman model and just explain again why I feel this is so important. We've been told, and a lot of people in the NPA, probably the majority of you listening, think of light as a thing that travels through space. And I know you've probably heard me say this before. I vehemently object to that assumption. I believe there are constants that we see in physics, and we attribute those constants to the particle. For example, Planck's constant or Planck's constant. We say, hey, that's an angular momentum. It's due somehow to something to do with the internal structure of the particles. Everybody agrees with that. We understand that the electric charge constant is some property for some reason that's quantized. Every particle has that same number or integer quantities of it or thirds of it or something, but it's all related to that special number we call E, and we attribute that to the particle. We also have Boltzmann's constant, which maybe is a little more nebulous, but in my mind, in my view, again, when I just talked about entropy, it's telling us a little bit about it's the how should I say the scaling factor, the number that tells us how much particles are interacting with other particles. So again, it's a property of the particle. So I keep coming back. All the units we have are going to be based on 5. We're going to have to pick some set of 5 constants to define any unit system, because in the SI unit system we pick mass, length, time, charge, or it's actually current, and temperature are the 5 that we use, and all other units can be based off of those 5. We could pick some other basis. I hope everybody understands this. The basis I like to choose are what I think of as the natural basis, and that would be angular momentum, which gives us the h nu energy, Boltzmann's constant, which is entropy, which gives us the kT energy, charge, which gives us potential energy, QV or EV, and then finally the fourth energy is mc squared. Well, here the constant is c squared, and the variable is m, and I think of that as translational energy. So those 4 constants, c squared, k, Planck's constant nu, and E, those 4 are the basis of my unit system. The 5th is energy itself. And we could choose energy. I would actually prefer to choose energy, but we often choose mass. That can be the 5th thing, because mc squared. That's fine. As long as we choose 5 independent things, we have to choose 5 independent constants. And then all of our units, all of our other constants are based off of that, or we're going to have unitless constants like the fine structure constant. So basically, we're going to be able to derive all our units from picking 5. So I'm saying now we've shown that all these other constants are attributable to the particle. So it just makes sense that C, the constant C, is attributable to the particle also. It's not a function of some property of space. There's no police out there that's saying that there's this thing called light that moves through space at some speed that we don't know why, but it does. No, it's a property of the particle that is reflected in the medium that we choose to think of because we have to, in order to account for stuff, we have to attribute fields and energy and all these kinds of things, and we call that light moving through space. But in fact, what's moving at speed c is stuff within the particle itself. Okay, that's really critical to understand, and the Bergman model and the common sense model show this. And they use, in fact, here's the idea, and I've shared this before, but it's background. I have to make sure people get this before I can move on. And it's basically Ampere's law. Ampere's law, which I'd like to expand to Ampere's principle, because I think it's larger than just its application to electrodynamics. People are thinking narrowly, and I'm thinking much more broadly. Ampere's principle is the same principle as Bernoulli's principle. It's the same principle as the pinch effect of Langmuir pinch effect, or the whatever pinch effect, the Robertson whatever. In fact, it ultimately is responsible for gravity. It's responsible for all forces of attraction, and it is this principle that when something flows, an increase in the velocity of that flow with respect to its environment requires a pinch. A time change is inseparable from a space change. So when you have water flowing through a pipe and the pipe constricts, the water flows faster, because the same amount of matter has to pass through each adjacent cross section. Or when you put your thumb over the hose, the the water flows out faster because the same amount of matter has to go out that hose as is going all throughout the whole hose, or there'd be a buildup of matter. Likewise, you can reverse that and say when the water is flowing down the waterfall or flowing, down your sink, it actually pinches because toward the bottom it's flowing faster because gravity's pulled it down than it is flowing toward the top, so it pinches. Okay, and so that's the principle of what I call the principle of translation, Ampere's principle, which is Bernoulli's principle. When the air flows over the straw, the pressure is decreased and the water flows up the straw. You've all seen that. It's the same idea. The motion itself causes the attraction. Okay, and this is key to understanding. And so that's basically Bergman's idea. I mean, he does it in a different way by calculating inductance and things like that. But fundamentally, that's what's going on. The stuff has to be moving in order to pinch in and bring in other stuff. If you have a subway train whizzing past you, you'll feel sucked into it. You've all hopefully felt that, and you know what I'm talking about. When something moves by you fast, you're moved in, and we know that and we experience that. So what I'm claiming is ultimately all forces of attraction are based on that, and that repulsion is just natural. That is a natural consequence of matter. Two elements of matter cannot occupy the same space at the same time, and so they're naturally repelled as they get closer and closer together. They're repelled from each other. This is the opposite of our thinking when we have what I call a gravity-only mindset, and that is we have to think of gravity in a totally different way. It is a second order and a third order effect due to the structure of things. That's why we need to study structure. That's why this is so important, what I'm talking about. Because again, in Dr. Lucas's model, and I don't think he's got all the details worked out yet, but I do think he's got the right idea. And that is, for whatever reason, atoms are structured so that there's a positive nucleus and a negative shell. And that's the thing I want to find out. Because if we can find that out, we know why we have gravity. Because, again, two atoms are going to have a repulsion between the negatively charged shells. A repulsion between the positively charged nuclei, but also an attraction between the opposite shell and the nuclei of the other one. And we're going to get two of those. So we're going to get two repulsions, two attractions, and they don't quite balance. There's just a slightly net attraction between them. And that, in my opinion, is gravity. In other words, gravity is a systemic force. It's not a net. There isn't a thing called mass that pulls things together. It has to do with the whole structure and system of the atom that is creating the force we call gravity. And while I'm at it, I kind of asked this question earlier. I believe charge is also systemic. There is no such thing as positive stuff and negative stuff. There are only two systems of motion, right-handed and left-handed systems of motion, which for whatever reason, and this is the thing I'm very intent on wanting to find out. I want to show this. I haven't done it yet, but it's important. Somebody's feeding back. I'm going to pause everybody. Hang on a second. Just give me a minute. Okay. Okay, I just did mute all. Hopefully everybody can hear me. And if you want to be heard, go ahead and unmute yourself. I don't have a problem. But, okay, so where I was coming from on this is the forces. We get really down some rabbit trails when we start thinking of mass as a thing. And we start thinking of positive and negative charge as things. When we start thinking of them as systemic and they're due to the fact that there is structure in the way things are moving, then that changes everything. And I'm hoping that I can convince a few of you that this is the path we need to go down. And then so my passion now, I hope I've made the case, is to study that structure. How can circuits loop around in themselves? How many different ways are there for them to do that, and so on, so that we can find the models that actually describe the neutron and the electron, and once we've got those building blocks in place, my belief is that we're going to just, if we can figure out helium, if we can get that far, then the next shell is going to be a piece of cake by comparison, because we've got the building blocks in place to figure out how to build the whole periodic table. And then from there, of course, we can then put molecules together in combinations and have the information to be able to understand and synthesize virtually any material we want, based on the characteristics we know that things have. So this is very powerful, potentially. But I am still not even to first base yet. And I'm just confiding with you. I mean, this is some difficult stuff. And I don't have somebody to tell me this is what you ought to do, because I don't know. And David, I've spoken with David Bergman on this, and he said, I've been working on this stuff for 20 years, and he doesn't know. He's shooting in the dark. How do I find this stuff? But what I admire him so much for is he's putting the math to it. He's not just talking in broad generalities. He's actually sitting down and trying to put the math to it. So again, my passion, a couple of my passions is I want to figure out how can I actually create a model where I can calculate the fields of this model, I can calculate the energy, and I can put two of these models side by side, and I can see, when they're both right-handed, they repel from each other. When one's right-handed and one's left-handed, they attract. If I can do that, and then we can synthesize that in a lab by winding some coils, I have basically shown what positive and negative charge are. And that, in my view, that has the potential to overthrow what we think, a lot of what we think we know about physics right there. That experiment, if we could do it. But the problem is I don't know what that model is. I only kind of have an inkling of what it should be, but I need to find a way to do that. Likewise with gravity. I mean, in other words, before we can really, truly, totally, convincingly show what gravity is, we have to answer the question, why does positive charge go to the nucleus and negative charge go to the outside? There's something to do with the way this stuff is circulating, and we have to understand positive and negative first before we can answer why positive goes to the nucleus and negative doesn't. So that's my first thing. First, figure out what makes positive and what makes negative. Then, why do positive or negative go to the shell and the nucleus, and the negative go to the shell? I think that question can be answered second. I hope this is my strategy, if you will, where I'm trying to go with all this. So what I need now, again, going back to 2007, I've concluded that, first of all, that motion is what's keeping it in circulation. Second of all, that motion must be confined to a circuit. It must have a finite path length. My reason for saying this is, again, you've got a finite element, finite thing here, and you know that it's held together by its own internal motion. That motion cannot just go on forever. It has to eventually come back to where it started, and that's the whole idea. So it has to be circuits. So circuits are what I have to deal with here. And the other thing is, it has to obey it has to obey Faraday's principle. And I'll just briefly state what I think of as Faraday's principle. I mentioned earlier the water coming out through the sink, and that it pinches as it comes down. It does something else. It also starts to twirl, starts to twist around itself. And I know you've noticed this, and all of you have seen when circuits go side by side. Not only do they attract each other, but they also want to start twisting around each other in forming a chiral sort of thing. Why do they do that? That part of it has to do with Faraday's principle. And again, I want you to think more broadly than just the limited electrodynamics. I want you to think much more broadly than that. Ampere's principle is saying when something translates, when there's a change in the velocity with respect to its environment, then there's also a spatial change. So a time change, the change in motion, translation, is inseparable from a spatial change, the pinch. Those two things come hand in hand. You cannot have one without the other, and because otherwise there would be an accumulation of matter through the flow. Okay, that's the key insight. And even if the flow is stopped temporarily, like a capacitor, the buildup of matter is itself a flow. That's Maxwell's idea of the the building up of that matter, and then which eventually would discharge across that capacitor or across that dam in the water. That is itself a flow, the building up. So remember that doesn't violate the principle if you understand the principle broadly enough. Likewise, with Faraday's principle, there is a time change that is inseparable, logically connected with, cannot have one without the other, to a spatial change. And this took me a while to figure out. This took me a couple of years to think about this, but I finally realized that rotation, which is a time change, is inseparable from shear, which is a spatial change. And one way to illustrate that is with a merry-go-round. If you got two people sitting on a merry-go-round, the one on the inside is moving at a slower velocity than the one on the outside. So by virtue of the fact that you're rotating, you have a velocity shear between the one going inside and going outside, which is why when you start walking inside to outside, you feel this Coriolis type of force, because suddenly, you're moving with respect to your environment at a faster velocity, and you have to account, you get this jarring force because of the change in velocity, which is an acceleration. So that's essentially what it is. And likewise, the Coriolis forces we feel on the Earth. The Earth is rotating at the equator at a faster velocity than it is toward the poles. And so when matter moves toward the poles or towards the equator, it's going to experience these Coriolis type of forces. They're real forces. They're due to the fact that velocity is actually different in those two different places. So I don't like the word fictional. I don't think that's useful or helpful. Those forces are real. If you've been on a merry-go-round, you know that it's a real force. So anyway, that same principle is responsible for what's going on in the twisting of the water that's coming out of the waterfall or your faucet, and it kind of hit me, believe it or not, this morning. There's actually a circuit going on, and this whole flow is part of a circuit, and you have to see the whole circuit in order to understand the twisting. What's going on is it's coming up from below the water, coming up to your sink from below, and then it's coming through your sink, and then it's coming down again. That's forming a circuit. And now when it starts to go faster, okay, it wants to do like what the figure skater is doing. It wants to pull itself in, and so it's trying to do that, and that's why it's twisting around when it's coming. It's pulling in simultaneously due to the fact that it's speeding up, but it's also twisting around because of this angular momentum idea. It's trying to do that, and there's an evidence that's for you that what's going on at the bottom of that stream is interacting with the whole stream, the entire circuit. They're not separated from each other, and it's doing this thing where it's wanting to twist around, and that is the cause of it. I hope that makes some sense. That's the best illustration I could make to try to explain Faraday's principle in a broader context. Faraday's principle is the same thing as conservation of angular momentum. It's the same thing that we see in the Kepler's second law, which is conservation of angular momentum. And by the way, Kepler's third law is inseparable from the Amperian principle. If you think of it in the broadest sense, it's the same idea. And I don't want to get waylaid from that, but these principles are very powerful. And when we understand them, the principles, then we can associate that each of these. There's actually 4 principles, 5. They're each associated with the conservation of these 5 fundamental ideas, which are angular momentum, charge, gravitational potential, c², okay, and entropy, believe it or not, as well as energy. And each of these 4 types of energy I've shown this in other talks I've had, are related to the 4 Maxwell's equations. And I've had some flack from people saying, well, Maxwell's equations don't explain everything. I don't know. And so I've kind of backed away from saying Maxwell's equations explain everything. What I mean are that the 4 principles that are associated with those 4 equations are sufficient to explain all of physics. I do maintain that, the fifth being conservation of energy itself. Anyway, I don't want to get too wrapped up in some of that, but I do want to talk about the fact that circuits are important, and because there are circuits, okay, this is really profound. I associate this with the law of entropy. Okay, and the equation I associate it with is the gradient of the magnetic field is zero, which is another way of saying that magnetic fields are closed loops. Okay, because they're closed loops. Closed loops are really special in a lot of ways. If you're going to have a closed loop next to another closed loop, you're going to have a shear. Think about it. I mean, if they're going this way, they're going in opposite directions, then you've got a shear of the one is going this way and one is going that way. You've got a shear of the magnetic moments, and if they're going the same, then you've got a shear at where the two meet, where the two hook up. In fact, you're getting an eddy current going in the opposite direction where the two hook up. Maxwell actually built a little thing that kind of showed this, where we had all these things spinning around, showing that when you had two things spinning around, you're naturally going to get something else spinning around in the opposite direction, which is an eddy current. And you're only going to get so many of those eddy currents, and those are going to form eddy currents of eddy currents. And it's just a logical necessity, because Faraday's law says that shear is inseparable from rotation. Rotation is inseparable from shear. I hope that makes some sense. This is a profound, important thing to understand about closed loops. Closed loops have this principle of shear, and in fact, the shear is part of what's necessary. Getting back to the very first question, what is a particle? What am I searching for? I'm searching for something that has shear along its pathway. Okay, because what I'm trying to find is models for particles that have something within their cross section that holds them together. If I were to have, let's just say, David Bergman's first model was just a line, what I might call a one-dimensional model. Then he expanded that and said, no, it's really a sheet on the surface of a torus. Okay, so all the charge was using this model. Let me get my little pointer. Where's my pointer? There we go. Okay, all the charge is spinning around this torus. Boy, it's really jerky. Can't make it spin real well. Okay, but anyway, it's spinning around along this sheet. And we realized, well, that's not quite right. The thing that bothered me, there's two things that bother me. First of all, there's no such thing as an infinitely thin sheet. It's got to have some thickness. So he said, all right, well, it's got some thickness, but it's real small. But the problem is that you're going to have then two elements next to each other that are moving exactly side by side with no shear at all. And by virtue of that, what that means that they're essentially not moving with respect to each other, and that's not acceptable. They have to be moving with respect to each other, so they can't just be going along side by side. You understand? Again, this is going back to the principle that I shared earlier. We only tell whether something is moving with respect to other things. So if everything is moving along exactly at the same way along this path, then it's not moving with respect to its neighbors, and it's going to be repelled from its neighbors. It's not going to be stable. And as much as I love the model, I could not accept that part of it. There has to be some kind of shear. In other words, these things have to be moving along the cross section so that they're intertwining and doing all sorts of interesting things. So that's a real problem that I had with that model. Well, then David said, all right, well, no, it's not just going around on this sheet, but it's actually going around on this sheet and simultaneously twisting around on the sheet, forming so that the path is sort of slinky-like. And then that's moving a little bit better in the right direction. That's taking into account some of this shear that has to take place, and is also satisfying, the idea. Here's another way of saying the same thing, is that if the motion is what's binding it together, then there must also be motion around the cross section, okay? Or the cross sections would fly apart from each other. So there has to be that kind of circulation too. I hope that makes sense. There's a number of different ways to illustrate that idea, but it's really important that there be shear. So we get these springy kinds of things. So this is an example, this trefoil knot, which is basically a torus knot. I hope you can recognize that this torus that I made it with Mathematica is exactly the same path, and it sits on the surface of this donut. Okay, so think of the trefoil knot, the center of the path is the same as the path on the surface of this donut. Exactly the same. All we have to do is just change the thicknesses. So that's real important that we understand. Okay, so there's got to be shear. There's got to be this twisting. Well, how much twisting? How much twisting is enough? And how are the paths? Can we have two paths side by side that are twisting in the same way? That's not good enough either. They've got to be. In other words, I can't have just a whole bunch of trefoil knots because then those trefoil knots are, spaced out along the surface of this donut because they're not moving with respect to each other either. So I hope you're beginning to understand the difficulty that I've been agonizing over for 5 years. How do we come up with a model that satisfies all the requirements? Well, along the way, I made some discoveries that I wasn't really looking for, but one of the really important ones is that that I can get from. Let's just going back to this torus knot. Okay, it turns out that if we take this torus and we spin it in different ways, and we do all sorts of different things, and we add up contributions from different toruses, I can get any closed loop circuit I want. And that was my discovery about a year ago, which I presented. It's called Fourier closed loops. I presented that at the conference. And the idea, I'll just try to summarize it in a nutshell, is that I can take any closed loop, no matter how complicated, and I can break it into components. And, well, first of all, I can break it into an X component, a Y component, and a Z component. So the X component is going to be a signal, which is going to be given in terms of this parameter that I'm following for the whole circuit. And I can normalize it so it goes from 0 to 2 pi. So I've got a parameter that goes from 0 to 2 pi in the X direction, the same parameter and that goes in the 0 to 2 pi in the Y, and the same for the Z. And then now I know what I can do with that. I can do Fourier analysis on it, and I can break it into harmonics. So I'm going to get a first harmonic, I'm going to get a second harmonic, a third harmonic, and so on. I can do the same with Y and Z. Then I can add them back together one harmonic at a time. So I can take my X harmonic, Y harmonic, Z first harmonic, add those together, and lo and behold, I get an ellipse. Because basically what I have is a signal that's oscillating with the same frequency, and but it has a different initial condition, a different phase angle, if you will, and a different magnitude. So I've got an initial condition and magnitude in X, initial condition and magnitude in Y, same in Z. I've got 6 parameters, and lo and behold, those 6 parameters are equivalent to the same 6 parameters necessary to describe an ellipse with the same center in space. Those 6 being you can think of it as being the Euler angles to get it in the right orientation. That's 3. 1 to rotate it into the plane, 1 to rotate it onto get the major axis lined up, and then the third to line up the minor axis, if you will. So that's 3. Then the 3 others are the major axis itself, the length of it, the minor axis itself, the length of it, and the phase, the starting point. So I got 6 parameters for my end point. So it turns out for each of these components, I can break it into an ellipse. And then furthermore, I can break an ellipse into 2 circles. So no matter how complicated my initial thing, I can break it into a bunch of circles. So it's like all I got to do is figure out the circle, and I've got it all. I mean, that's pretty cool. So now I just need to figure out a way to come up with a structure that satisfies all these constraints that I'm interested for a circle. I don't have to concern myself with this complicated torus knot. The other thing that's pretty interesting is these are dynamic structures. Okay, they're not static. They're static in the sense that if every element, if you think of this as charge, or what I call primal charge, it's not positive or negative yet. It's just stuff that's moving around. Okay, if this stuff is moving around in the at speed c, and again, I'm sorry for kind of. I don't make every point clear. There's so many elements here. C is the important number, and I was talking about this about 30 minutes ago. What C actually is. It's the idea that stuff has to move in order to stay together. But if it were not moving, it would fly apart. Okay, and yet if it were to move completely, it would come together as a dot. So there must be some finite velocity at which it remains stable. Okay, and for whatever reason, there is one specific finite velocity at which all particles remain stable, and that is c. In other words, everything is moving at this special speed c relative to its environment. That's a key thing. And Dr. Keene has helped me to understand that rotation is not is an absolute thing. Things don't necessarily rotate with respect to the rest of the universe. Actually, what's going on is things are rotating with respect to other things in the system, and that is related to this idea of shear. Shear, the inseparability of shear with rotation. And so, in other words, again, going back to the merry-go-round, the very fact that that there is shear, which is measurable, you can feel that shear stress. That is indicating that there must be rotation going on. So if the rest of the universe went away, and I experience, and I'm on this. There's nothing here but me in this merry-go-round, and I could detect that there is shear going on all across this this merry-go-round. I could say without equivocation that merry-go-round is rotating. Okay, it has nothing to do with everything else in the world. It's due to the fact that there is this shear going on inside the merry-go-round itself. That was a key insight, and I thank Professor Keene for helping me to see that, because that led me to something else. And I hope this isn't seeming too random and rambling, but this is getting to the models, why the models are so important. But anyway, there's a well-known thing in acoustics that says that the shear modulus of a material divided by its density, which we can call rho, it's G over rho. So shear modulus has the units of energy density, and rho obviously has units of mass density. Okay, the ratio of those, which is the same as the ratio of energy to mass, is equal to the propagation velocity, the sound propagation velocity in that medium squared. V squared. There we see V squared. And I said, that equation looks an awful lot like E equals mc squared. So G, which is the shear modulus, equals rho V squared is essentially the equation. So it's energy density and mass density, but hey, equals mc squared works there too. In fact, it does. We could say energy density equals mass density times c squared. And I'm thinking to myself, now does this have something to do with what I'm searching for? And by golly, I think it does. And in fact, it's a way of understanding E equals mc squared in kind of a new light, again, with this delta factor that I talked about earlier, that there's a rotational factor as well. That is to say that the propagation speed, the speed at which this stuff flows around my complicated circuit, has got to be equal. That velocity squared is equal to the energy, the shear modulus, time or divided by the mass energy. Okay, the amount. In other words, the mass. I don't think of mass as a thing. Mass as a property. It's how much is this property? How much is this particle resisting changes in translation? Okay, if it's resisting that, if it's influenced by external fields to that extent, then that is its mass. So profound, bingo, huge light bulb for me on this one. Hope some of you get this, that the shear modulus is a measure of its energy in one sense. The resistance to motion is a measure of its energy in another sense, and those two have got to be equal, if you will, are related to the propagation velocity, which is c. In other words, everything has to be shearing so that there is a shear modulus within this structure, so that has to be balanced or related to precisely the the amount of resistance that when we call it mass, when we measure its mass, those things have to be connected. So that was a huge clue to me that, again, sort of a new way of understanding E equals mc squared, but also a way of understanding this whole propagation thing, and maybe a way of understanding what C is in terms of this circuit. Okay, so now let me go back to the model itself. There's something called Villar-Sauce circles, which I'm going to show you later, and it's basically a circle where, going back to this donut, and I can't believe I've been at this for an hour already. I hadn't even gotten to the second slide. But okay, going around this donut, we're going to go around the donut one time. Forget the picture that's in now, but imagine that as I'm going around the donut one, I'm going to go around the cross section once. Let me see if I can find that. That's called a Villar-Sauce circle. And incredibly, here's one. This is a Villar-Sauce circle. The white, the Sagnac Award here. You see the white is going around the circle once as it goes around the cross section once. And so does the silver, so does the gold. I mentioned this, I think, last week. What excites me about this is these are pure circles. They have no, what Professor Keene calls, there's no Frenet-Serre torsion. There's topological torsion. In this case, it's left-handed torsion. Because if you follow with your thumb along the path with your left hand, your fingers will curl in the direction of the twisting. Okay, and if you put it in the mirror, you'd get just the opposite. It's going to be one or the other. Everything's going to be one or the other. I don't have my rings here with me. They're in Albuquerque too. I left them in my suitcase, but to play with those rings, those of you that know me have probably seen me show those before. But that's called a Villar-Sauce circle, and what's so important about that is that if you think of the paths of each of these circles is actually sitting on the torus, sitting on the surface of another, larger or main torus. Okay, so these three are all sitting on that circle, and they have the same radius as the torus itself. That is a critical, key, really important observation. Villar-Sauce circles. Well, okay, now I've got these. I'm not imagining these as fixed things. They're fixed, and I was interrupted myself as before in saying that they're fixed in the sense that if they're stable, each element in the path is going to be replaced by another element just like it. So it appears to be not moving. Okay, it's not moving in that sense, but in reality, everything is moving within this structure. Okay. So now that being the case, now I can take the whole ring and spin it. Okay, I'm going to take this whole plate and spin it. In fact, Bob DeHilster built me something. It never did work, but we got close. That did something just like this, where we had essentially thought of them as Christmas lights going around this Villar-Sauce pattern while the whole thing is spinning. So while if it's not spinning, it takes, let's say 1 unit of time for it to spin around. Now, if it's spinning half as much in the opposite direction, it will take 2 units of time for it to do that. So it's going to slinky around the structure, in order to get back and complete the circuit. And that's really important. It's not. In my view, this is what a photon actually is. It's a change in state. It's just like what we call the strobe effect, and we've seen it in Lissajous shapes. We've seen it in. I've got a whole list of things that it's similar to. I believe all quantization results from this change in frequency. We've got. In 3D, you're always going to have things that can move in one direction and also move in the perpendicular direction. There will always be 2 directions of motion for any finite object, and that will always create shears, and that will always create this opportunity for quantized changes. And this quantization of change, in this case, is what we call a photon. There's no such thing as a photon. There's only a quantized change in the state of the way things move. And I hope that illustration made the idea. Let me see if I can find this. There it is. This is the thing Bob built. Now this is a little different because now here the ring, the charge, the Christmas lights are spinning around the cross section, and then we spin the whole object around. The whole table is supposed to spin around, and then it creates these slinky-like patterns that look like they're on the surface of the donut. I hope you can kind of visualize that. I really wish we could build this. Jeff Cook has it now, and I was hoping, he's so busy with all of his stuff that but I'm hoping someday somebody will actually build this and make this work. I think it'd be really cool. But hopefully you've seen things like this where you see the interaction, and then like the roulette wheel at Las Vegas, it gets synced up with the 60 hertz light bulb, and it looks like it's not moving at all. And then as it slows down, it's going backwards. And then as it slows down even more, bam, suddenly it's going forward, only much faster. That quantized change, we call it the strobe effect, is because now we're not seeing the one that was there previously. We're seeing the one that's moving forward next. Okay, and we say, gee, that's just an optical illusion. No, yeah, it is, but it's actually fundamental to the way matter works. I believe that effect in all these quantization things, we see it in, I said Lissajous shapes, on a oscilloscope. We see sorts of different ways of getting these quantized things. That is responsible for one of the first questions I asked way back when, and that's in this model here. Here's David Bergman's model of the spinning charged ring. And as you can see, this one's spinning around. It's going around 3 times. He says K equals 3. And as it's going around the torus, which is the bigger circle, he's got the loop, the fiber, going around 3 times around that. And I was saying to myself, well, how can it get from 3 to 4, or from 4 to 5, or from 3 back to 2? How can it do that without untying the knot and then retying it? And that's not allowed. And the answer is, these are dynamic things. They're moving, and when they move, they can change state by virtue of the motion itself. They go out of phase, and then they come into phase in the next state. There's a quantized change. This occurred to me back in 2007. I've been trying to share this idea with people for a long time, and I don't know. I think it's incredibly important, but I can't seem to get a lot of other people to see that as being really, really fundamental and really, really important. But anyway, that was the key insight, and I remember the night that hit me. It's like I thank God for showing that to me. I mean, that's all I can say. It was just this idea that it doesn't get tied and untied. It is virtue of the dynamics and the fact that there's a change in the rotation of the overall thing that causes it to change state. So I'm going back now to the original thing that I was showing. This trefoil knot is no different mathematically from the Villar-Sceaux circle, which just goes around once, because all I have to do is rotate it 3 times as much to be able to get to be able to get that rotation to look the same. I hope that makes sense. So if I can figure out the Villar-Sceaux circle, I can figure out the trefoil knot. That's a piece of cake. The problem is figuring out the Villar circle. I hope everybody gets that. And it's more than that, because not only can I rotate it in the direction that it's moving, I can also rotate it in the opposite direction. In other words, I can take my donut like this, and then I can spin it like this, and I get something called spherical rotation. Okay, so in other words, think of my donut here. I've got my donut, and it's wobbling like this. As it's spinning, it's also wobbling. If the wobble gets big enough, it'll actually be up on its end. And the way I like to explain, I apologize if this is something I've said before, but it's important. Spherical rotation is the best way I can describe it is, imagine an airplane starting at the equator. He goes up over the top of the North Pole, goes to the other side of the world, comes back down to the South Pole, and comes back where he started from. And he does this in 24 hours. Actually, 23 hours and 56 minutes, a sidereal day. Okay? Now, he says, I went in a circle, or pretty close. The Earth isn't perfectly round, but it's close. Okay, but now we're going to look at him from the moon or from outer space somewhere, and we're going to see the Earth turning, and we're going to watch him do it, and he's doing this in exactly 24 hours. He's going to go up over the North Pole, and by the time he gets to the other side, quote unquote, of the world, the other side of the world is where he started, and he's going to come back down and then come back up. He makes this figure 8 pattern, and it's all because we're rotating the object as a whole. Okay, so what I'm saying is all of these different paths and shapes can be actually created by various rotations, either in the plane or perpendicular to the plane, or different combinations. I can create any kind of knot just by taking my simple Villar-Sceaux circle and rotating the whole apparatus in a lot of different ways. So again, it just keeps coming back to, if I can figure out the Villar-Sow circle, I can figure out any structure. I hope everybody's getting this point. And so again, what I got here, this is 3 Villar-Sow circles working together. Here's 5. Here's 35 of them. Okay, that's what they look like. And interestingly enough, each of these circles passes through all the other ones. All 35 pass through the other 34, and they form beautiful patterns like this. So that's all these are, just a bunch of Villar-Sow circles. So Borromean rings is another way that things. This is the Hopf rings, which is the Villar-Sow circles, pass through each other. The Borromean rings don't. It is only in their conjunction that they can be made to. In other words, the 3 working together cause them to form a structure. If you take away any one, the other 2 are not actually passing through each other. That's the Borromean rings. There's a lot of interesting things about that, and actually Don Burdell's structures are related to the Borromean rings. Okay, so my passion is trying to figure out, first of all, what charge is, and developing a model for the electron and for the proton. By the way, I'll just throw this out. I believe that when getting back to this wobbling thing, the second rotation doesn't increase the energy, it actually decreases the energy, because there's a coupling going on, so that the particle that has 2 rotations, that has this spherical rotation pattern, is actually lower energy than the particle that's just in the torus. I believe there are actually 2 stable states, and this is just conjecture. I haven't proved this. This is just the model that I have in my head, so you know how I'm thinking. I believe that the lower energy structures are the spherical rotation ones, which is the electron and the positron. Those are actually lower energy. And that the higher energy ones, but they're smaller, are the proton and antiproton, and they're toruses. So the torus, the toroidal rotation, and the spherical rotation. And by the way, if you think of these as being Villar-Sow circles, in other words, let's go to the model of 3 Villar-Sow circles, like this Sagnac award here. If we think of that as a model, there's actually nothing passing through this very center. There's nothing there. They're all outside the center. So now, if we take this whole Hopf ring and spin it, to make that spherical rotation model, there's actually nothing. There is no singularity, is my point. There's nothing actually passing through the north and south pole, okay? Where there would be if it was just one ring. Everything would pass through that center point, and there would be a singularity there. Singularities are not acceptable. We have to have models that have no singularities. This model does not, because each of these are spinning in there. In other words, there's cross-sectional stuff, but there's nothing in the center of the cross-section. So that when the thing as a whole passes through the pole, nothing actually passes through the North Pole. And it looks a little bit like a sunspot. And I'm just wondering if maybe that's in a way what a sunspot actually is. It's a point where there's this charge, where there's charge circulating going in and out, but there's different fibers of it doing it in such a way that we get this point in the pole where there's a spherical rotation pattern, but there's also these other patterns coming into and out. We get this swirling. That's just conjecture on my part, but it's pretty interesting. And that's, again, kind of how my mind works. So, all right, I've said something about all of this stuff. I've talked about that already. Here's Don Burdell's structures. I played with some of these ideas. Again, I love these models, and I like to play with them. And I actually did, I think I showed last week, Don, a way to actually model all of these structures by showing that each of these paths fit on the surface of a torus. In the case of the tetrahedron structure, what I have the red, the blue, and the white path. Each one of them is sitting on a donut. One donut is centered on the x-axis. One is centered on the y-axis. One is centered on the z-axis, and they're going around this donut twice. And I hope you can see that 2 twists there. And so when you do that, you get a structure that looks just like this. And it turns out these 4 key points, the points where they want to come together, if they're twisted enough, if the donuts are thick enough, then they'll meet at this critical point where the 4 points of the tetrahedron. And well, I'll go ahead. I'm kind of rambling, but well, okay. I will show this in a minute, but before I do, I want to finish up with my point. Um, no matter what the structure is, and I love Don Burdell's stuff, and I love some of the models that Bill Hohenberger and some of the other people have put together. But we still have to address the question of not how the different components fit together, but what's going on along the cross section of one given component. That has to be answered first. In other words, if you just follow one path, it's finite and it has to have structure along that path. And again, I can model this structure as just being a path along a torus, which I can model in terms of a Villar-Sceaux circle by spinning it. So all I really need to know is what's the structure along a circle. Okay, I need to know that first before I can get this. I hope I'm making this point clear. Once I have that, I can build these. Okay, and now I'm going to take the time to show you what I showed you last week on Don Burdell's structures. I'm going to have to share my desktop, so let me see if I can do that. I didn't even prepare a file, and here is almost an hour and a half, and I barely started talking about some of the things I was going to talk about. So I guess I don't need to prepare a file. Okay, I can't think straight here. Hopefully you'll all be able to see this. Okay, this is what I was going to show, this lattice polyhedra, but I don't think I'm even going to get to that. So I'm going to show you the Burdell structures instead. Let's see. Where is it? Come on, where is it? Polyhedra. Well, can't seem to find it. Hang on, let me find it. Okay, hopefully all of you can see what I got here. Okay, toroids, Burdell, there's the one. Okay, all right. Now what I wanted to show, here's the model, and I showed this last week of these things. Now what you have to imagine, and I'm not showing, is that these paths are actually on the surface of a torus. Okay, so the green one's on the surface of a torus that's centered on the x-axis. I don't know if that's right. The red on the y and the blue on the z. And they're what I can do is this variable right here, which is psi, changes the thickness of the donut. Okay, that's all it's doing. When the donut is perfectly thin, then of course they're circles. Okay, and then as I thicken the donuts, then they twist a little around that, and they're twisting twice around that. And as you can see, they actually form Borromean rings, so that the green is inside the red. But if you took the blue away, the green wouldn't be attached to the red. And if you took the red away, then the green and the blue would fall apart. Hopefully everybody can see that. I'm trying to move it around at different angles so you can see the different angles. And then as I move it in, I eventually get to the critical point where these things cross. Beyond that point, we have where's that critical point? Is right about there, pretty close. Okay, that's where they cross. Beyond the crossing point, then they become what Don calls a structure, because if you look, for example, at the red path, you can see at any of those points that the blue and the green are holding it back, keeping it from springing out again. Okay, but what happens right at that critical point where they cross? That was what interested me. Those 4 points, it turns out, are the 4 points on here. Whoops. Now what I have here is a unit sphere and a torus meeting. And where they meet, those 4 points are on a unit sphere. So we know, for example, that the 4 points of a tetrahedron are equidistant from the center. So they can be positioned as 4 points on a unit sphere. So hopefully you can see my pointer. If I could put one of those points here. Hopefully you can see my pointer. One of those points here, and then 1 point here on the underside, and a 4th point here on the underside. So I get the 4 points of the tetrahedron. If I get the thickness just right, and I calculated that, what is that special thickness, where the 4 points of the tetrahedron are the 4 points where these meet. Hopefully everybody sees that. You see, it looks kind of like Saturn, and I don't know if I've got the thickness exactly right, but there is a special thickness where where those 4 points are going to be the 4 points of the tetrahedron. That's exactly what these 4 points are, and that critical. I've forgotten now. I calculated it, and I can share it with you if you're interested. But there is a critical point. Well, then I went on. I said I could do the same with the cube, except with the cube, I can't. Well, let me do the dual of that is the tetrahedron, and let me show. Is this the tetrahedron? Okay, let me see if I can find the critical point. Same thing with the tetrahedron. Whoops. Hang on. Oh, I'm not finding it here. Did I get the dual? Oh, here we go. Sorry, this is the tetrahedron. Hopefully you can all see this. Let me find that critical point. Oh, wait a minute. Why am I not finding it? Struggling here. Oh, I think I went too far. No. Shoot. I used to just get right to it, and now I can't seem to find it. Okay. Sorry. I'm not sure if I've got the cube or the tetra. Let's see. There we go. There's two of them coming together. Oh, for heaven's sakes. I've never had this much trouble. Okay. Okay, there we go. Why am I having so much trouble today? Not sure my problem here. Something get messed up here? I'm concerned that something's got messed up. Something is messed up.
Hey Greg, this is Robert Kemp. I think you may be doing something that's computer complex.
No. This works fine, but all of a sudden, this is supposed to be on the surface of a sphere, and they're clearly not. So something happened. Darn it! What a bummer. No. There's something got changed, and I don't know what. Oh dear. That's really strange. It's not working correctly. It's working fine for the tetrahedron, but it's not working right for, let's see if the icosa. The icosa is okay. Something got messed up for the cube. I'm sorry. Well, anyway, here's the icosa. And again, I've got six of these, and I'm twirling them a little bit 5 times. They meet up, and you'll see there's a critical point. It's a little harder to see with the icosa, but there it is. Come on, help me out here. Okay, I'm still not getting there. My point is that the critical points, if I could ever find, maybe let me try this. I'll try the dual. Good heavens, I've never had this much trouble. Wouldn't you know? Okay, there we go. I'm pretty close there now. Okay, this is there we go. I got it now. Okay, you can see this is the critical point. Hopefully you can see the points of the dodecahedron. So you can see the 5. You see the 5 points here. There's a critical point. There's a critical point. Critical point. They're coming together to form these patterns. And it turns out, again, returning to this, I didn't really mean to spend this much time, but well, let's take the cube. The cube, the octahedron has 6 points. They can have 3 points that meet on this unit sphere on the top. I'll get the thickness just right. 1, 2, 3, and then I can have the other 3 at the points in between on the bottom. 1, 2, 3. I hope that makes sense. And those 6 points, so 3 on the top, 3 on the bottom, can form a tetrahedron. So in other words, I can find a critical thickness, and for some reason my program got messed up, but there's a point where I can get that critical thickness where I can get that tetrahedron exactly. And the cube, I can't get I get 3 again also. But there are 8 points. The fourth point is the point on the top right here and the point on the bottom. So I get, if you can imagine a cube, let's see, I don't have a Rubik's Cube handy, but if I had a Rubik's Cube, I have a top and a bottom. I've got 3 points on the top, 3 points on the bottom. Those are, the top and the bottom are going to be on the unit sphere. All 8 points are on the unit sphere, but 3 are going to be intersecting right at this critical thickness. 3 are going to be intersecting right at that critical thickness. And so the cube, I get a beautiful structure with that. I showed it last week, and something screwed up with my code somehow, I guess. I don't know. It's possible I typed in a random character and it messed it up, but I don't see what it is right this minute. Well, I don't have time to worry about it. Anyway, that was a little bit of a tangent. I wanted to show you, and I'll come back to the, okay, I'll come back to my file here. Whoa. Okay. Come on, stop sharing. Okay, and bring my file back. Okay, hopefully you can see all of those. I'm sorry that didn't work better, but you can see, if you look at this diagram, you can see the twisting of the one structure. Unfortunately, they're not different colors as they should be, but you can perhaps take this one here. There's a path along here. It goes through that critical point, comes around there, and it twists back over there, comes back around here, comes up. Oh, it's easy to get confused. Excuse me. This one comes up there, through there. You're going to see it going around, weaving 3 times, coming around there, and they each do that. They weave 3 times. They fit perfectly on the surface of these toruses. So my central point is that this can be done with any shape. And to get Don Burdell structures, all we have to do is get a donut that's a little thicker than the critical thickness, so that it goes past that point, and then then the other circuits are actually holding it from coming back. And that's really the principle of Don Burdell structures. And then that program I showed you, I can flip it over, make mirror images. It's a shame it didn't work, wouldn't you know? But I've played with it many, many times, and it works great. So anyway, so again, getting back to the thesis, is that what I'm really interested in is understanding what's the structure going to look like along just a simple circuit. And this is another example of some possible models. And I did talk about this at the at the conference, Tom Lockyer's vector particle physics model. Okay, so Villar-Sault circles. Where do you start with all of this? Let me see if I can explain the problem. I can see that my time's running out, and believe it or not, I had a whole lot more to say. But there we go. So what I have here now are 2 Villar-Sault circles. You can have a right-handed one and a left-handed one. So that's what I have showing here in this diagram, just those 2. And there's a nice animation, and I meant maybe I could show this one next time I show desktop. There's an animation, if you look up Villar-Sault circles on Wikipedia, where it slices. Those 2 circles actually fit in a plane. And there's a nice little slice you can make. It was a real revelation to me to find out that the radius of this circle is the same as the radius of the donut itself. That is so important. I can't emphasize it enough how critical that is. That is opening a lot of things. Anyway, so then what I did was I said, all right, let's take just 2 rings. Okay, in other words, like I have over here, the blue one and the green one that sit on the ring, and then suppose they have thickness that's just enough so that they're touching. What is the path of where they touch? It turns out that when you just have 2, and I've shown this, that the path where they touch is exactly the center of the ring. I worked on that for a long time. It took me a while to figure it out, but it's exactly the center of the orange ring. Okay, so I'm looking at in other words, I've got a green ring that's thick enough to meet the blue ring, and I'm asking, what is the path where they're touching each other perfectly along the whole path, and what is the path of that ring? And it turns out to be the center of the orange ring. Is everybody understanding that? And the distance, obviously, between the green and the orange is the radius of the orange ring. And the distance between the blue and the orange is the radius of the blue ring. But the distance from the green to the blue is not just simply twice the radius, because those 2 then this was what was a surprise to me, that the angle that they meet at is not perpendicular. They meet sometimes at a funny angle, sometimes a right angle, sometimes less, and that changes throughout the path. And that was a surprise to me. I was going under the assumption that would be, they would be meeting at the same angle from each other, and they don't. So that was in itself was a really hard problem. The second problem that I solved was trying to figure out, okay, now what is the path where any two rings of my three meet? So again, what I'm seeing now is I'm seeing the ring, the orange ring, on which these three sit as a surface. And I want to know the distance between these rings because they fit perfectly the whole way around. How is it that they can do that? And they themselves, the point of where they meet, also forms a ring. And is that on the surface of the donut too? Where does that lie? It turns out it's not on the surface of the donut, but it's also not the one that is inside here. But it is the same radius. So that was an interesting revelation. Then I said, well, what if we have 4 or 5 or more? What happens then? Well, the problem is once you get 4 or more, then the relationship between all of the rings changes. There is no longer have each of the rings in contact with all the other rings once there's 4. I hope you can see, because the two that are opposite each other won't touch. And I for a lot of reasons I want them to touch. Okay, and so I decided that 3 was an important number. Another really interesting thing about 3 is if you go back to that, 3 is what you need to introduce 3 dimensions. If we go back to way at the beginning, that Don Burdell's structure, that tetrahedron's got 3 circuits. And going back, boy, this is really slow. Wow. I'm trying to go back to the very beginning, that trefoil knot. The trefoil knot, which is going here. Goodness, it's slow. Wow. Come on, get there. One more. There we go. The trefoil knot. Hopefully you can kind of see, if we make the trefoil knot thick enough, you'll see that it kind of comes in. It almost forms an axis, a 3-dimensional axis with one, this say being the X direction, this being the Y direction, this being the Z direction. And this is again sort of confirming the idea that that there's 3 dimensions associated with this. You can maybe see it in these 3 rings here. Think of this as being the X direction, where this one comes in as being the Y direction, and where the third one comes in as being the Z direction. I hope you can see that. Inside you get this, and this. They form sort of an axis there too. 3 is what you need to get 3 dimensions. So there's another reason why I'm really emphasizing the number 3, and there's several why I believe that's the case. 3, it turns out, then, is also the number upon which to build a fractal. Whoops. Oh, here's some more examples. Whoops. Here's some more examples of Villar-So circles. I found on the internet. Here's a guy that built a coffee table out of just a bunch of Villar-So circles. I thought that was kind of cool. And here's some Villar-So circles. He's got 3 of them built on, I don't know what those things are inside. And here's a couple of structures that have Villar-So circles, green ones going in what I might call right-hand, let's see, those are left-handed, and the inner ones, I guess, what are they, sort of tannish ones inside are right-handed, and the two together can form a structure. Now that's an interesting idea. Can we perhaps build something that is somehow both right-handed and left-handed within itself? I'm open to that. That's a possibility for some kind of an opening, for some kind of a structure. Here's a guy that built something out of, again, right-handed and left-handed. Again, the right and left-handedness has nothing to do with the circles themselves. It has to do with the way the circles are put together. That's so important that I make that clear, the way it's related to the structure as a whole. So, but anyway, there's right-handed and left-handed ones. He wove them together into this beautiful pattern here, Villar-So circles. So there's a couple of ways to help you see sort of what I see when I think of Villar-So circles. There's many, many things you can do with them, but I'm returning to just the simplest problems. So first problem was figuring out, what happens when 2 rings are touching. Where do they touch? The reason I need to know that is because I need to know how thick the rings are. I know, in other words, given the thickness of the orange, what is the thickness of the green and the blue so that they just touch? I had to know where they touched in order to be able to figure that. Okay? And it turns out in the case of this one, the thickness of the green and the blue is precisely the thickness of the orange. And that was a surprise. Now, but in the case of 3, I hope you can see that the outer rings are going to be less thick than the inner ring on which they're part of the surface. And that ratio, I have not figured that out yet. I'm working on that right now. I've been working on this for a long time. It seems like it's something you ought to be able to whip out and have it a really challenging problem. But now what I want to talk about is the next level, because this is, okay, way back in the beginning or somewhere toward the beginning of my talk, I said there's got to be shear. There has to be this constant motion across. It's not, and I need to find a way, and it's not in how many times it goes around. It's not how many slinks there are, because I can take and rotate the whole blasted thing and get more slinks. So that's not the issue either. I only have to say I want to get these paths so that each of these paths turn out to be circles. Okay, so in other words, they're happy to continue conducting at this special speed without any change in their path, without any Frenet-Serre sort of change. And yet there is shear. And that shear has to be going, it has to be topological. It has to be the way these things are relating to each other. Can that be done? And the answer is yes, it can. And here it is. This is so exciting for me, and I just can't seem to get anybody else to see it as I do. But you understand that the fact that each of these rings has the same radius as the original ring means that now I can take each of these structures and start all over and do the same thing and put 3 rings on those. And then I can take each of those 3 rings and figure out how thick they need to be, and then put rings on the surface of those donuts, and keep on going. And I can build a fractal structure. What I'm going to end up with is an infinite number of rings that have that all pass through each other. Every one of them passes through all the others. And yet it has thickness, because no longer do I have a situation where everything's just on the surface. In other words, if I just had an infinite number of these Villarceau circles, but they're all on the surface, then there would be no thickness. I just have basically David Bergman's ring, which has got charge circulating around the sheet of charge on the surface and spinning around the cross section simultaneously. That's basically having a whole bunch of Villarceau circles smeared around there. And I wouldn't accomplish what I'm looking for. I need some way to get depth. I need some way to have movement into the circle, into the torus, and out of the torus again without... in other words, it's not okay for me to have like just a bunch of layers, because then there would be no motion between the layers. That's unacceptable. There has to be shear between the layers too. I hope everybody's getting this. And so I need a structure that does this. And by building this fractal structure that I'm talking about, I can get, not only can I do that, but I can introduce every element in my structure is going to have shear with every other element, but there is going to be depth, because each of these things are going inside and outside of each other. Okay, and every element is a circle. And it's the same circle as the one I started with. And I don't know, that's just so incredibly beautiful to me. I just feel like it's got to be right. But the problems are tough. Once you get to the second generation, you see then there's thickness to, okay, in other words, the rings that sit on the surface of the white one, for example, are going to themselves have thickness, and they're going to run into the ones that have thickness on the ones the silver one. Is everybody seeing that? And so I have to make the white one thinner so that it doesn't quite touch the silver and the gold one, so that the ones in the white, the ones on the surface of the white one just touch the ones that are on the surface of the silver one. And then when I get to the next level, I have to make everything smaller again, so that the ones on the surface of those don't run into the ones that are on the surface of the other ones. I hope this is making some sense. But once I can figure out the method to do that, then I'm hoping it's not going to collapse on me and everything's going to have zero thickness, but there'll be an actual finite thickness. Okay, it'll be, but I don't know what that is. In other words, so that I know, given one level of thickness, I know what the next level of thickness has to be, and it's going to have a progression to it. Eventually, it obviously gets down to infinitesimal, but it's got It's got a sequence to it. And that's what I'm after. That's what I want to know. Because once I know that, then I've got something that's got structure, and I can figure out whether it's stable. And here's how I'm going to do it. I'm going to just take, I can take a circle, an infinitesimally thin circle, and I can calculate the magnetic field associated with that and the electric field associated with that. And then I can figure out, based on all of that, its energy. And that's going to be, I'm going to have energy spread out through space, which is infinitesimal in the sense that it's being attributed, that it's spread out through space, but it's also infinitesimal in the sense that each contributor, this little ring, is an infinitesimal thing to begin with. So I'm going to have to do actually a triple integration. It's going to be an integral of an integral of an integral, but I'm going to add up all these components. In theory, it's not that complicated. I mean, because it's just a circle. And so I should be able to calculate this thing. Once I have that, and I'm hoping that this structure then will do a couple of things. It'll be stable, number one. That's important. Number two, it'll answer the question, where does positive and negative come from? Because I'm hoping that two of these structures side by side are going to attract or repel based on whether or not they're right-handed or left-handed or how they are. And I'm still open to the idea that the substructures could be left-handed when the structure as a whole is right-handed. I mean, these are things I need to play with and that I'm working on. But the math is hard. I've been working on it for a long time. And all I can say is if somebody gets what I'm doing here, I'm hoping that maybe you can join me. I need somebody who's really good with math to help me figure out some of these problems. So I can't believe it's been an hour and a half already, but what I'd like to do is share my desktop with you and show you some of the things that I'm working on in Mathematica, so you can kind of get an appreciation for some of the difficulties I've had. And again, I don't work on this night and day, and lately I get so darn busy, with the working on everybody else's paper that I don't really. Sometimes 6 months goes by and I don't do anything. But, then I come back to it and I kind of have to start over. But I keep coming back to it. And let's see. I don't know which file is which. I got a whole bunch of files here. Let's see. Which one's this one? All right. Okay, yeah, this is the one I wanted to show. All right. So hopefully, can everybody see my desktop? Does somebody let me know? Okay, Don says okay. All right, so you can see this picture right here. What I have here it looks like just circles, but it's actually a donut. You have to visualize the donut. The center circle, which looks kind of like, I guess it's sort of gold color or brown color. That is the center of the donut. And then the blue and the sort of reddish purple ring, those are Villarceau circles on the surface of this donut. And this parameter psi is the thickness of the donut. Okay, so as I make the donut thicker, they spread out more. So, and as I make the donut thinner, of course, they all more or less merge into one and becomes just a circle. Okay, everybody kind of getting that picture? So the question that I was asking, and I mentioned earlier, is I want to find the point on each circle that is closest. Where is the point where a circle, the red circle, is touching the blue circle? Okay, and it turns out that point is the point on the brown circle, the center. That was a real surprise. I didn't expect that, but that does turn out to be the case. And I don't know if it's obvious, but what I was trying to say earlier is that the line, if you were to draw a line from the point on the red circle to the point on the brown circle, and then draw another line from that same point on the brown circle to the blue circle, those two lines would not necessarily be parallel. That was a surprise. So what these two inner ones are showing is the distance from the red circle to the blue circle. And I thought that those distances would lie on the surface of a sphere, but they don't quite. Not quite. In fact, they get more obscure the thicker it gets. That's what those are showing, and it also shows kind of that figure eight pattern I was talking about earlier, with the spherical rotation. It's like spherical rotation, except it doesn't quite go all the way up to the pole. Is one way to think of that. Anyway, what those are showing is the direction that. So it's the same distance, but it's a different direction. What's the direction that that line from, which I call little r, from the red to, or from the brown to the red? What direction is that pointing? And that gives us the inner blue circle, and the inner green circle would be the line from the brown to the blue. Okay, I was real interested in that, trying to figure out what that is. I hope that makes some sense. I would like to find a better way to show this stuff graphically. I find because this stuff is really hard to visualize, and if I could get some really nice graphics, and I'm pleading with somebody to help me to show these things, because they're important and they're interesting. But if I could show the outer surface, and then just lightly, so you could see that these things in fact lie on the sphere, and then show the line from the brown to the blue, and then show how that fit, how that makes a curve. It's really hard to see looking at these pictures. I know what I'm seeing, but you might not, and it's hard for me to describe it. That's why I need better visualization tools to do that. But anyway, that's the first step. And again, this is, I don't know why I did this. This is just showing those two outer circles. They change with the thickness of the donut. Now here's the donut itself. So what you're seeing here now is the two donuts. You're not seeing the inner donut, you're seeing the two outer donuts, and you see they fit perfectly. This was a huge victory for me to be able to figure this out, to get them to fit perfectly. The point where they touch is the center point of those first two donuts. And now what this parameter does is change the thickness. So I can make it thicker. Doesn't matter how thick I make the donuts. They still fit perfectly. Okay? Hopefully you can see that. I can make them thinner. I can make them thicker. Whoops, doesn't matter. They fit perfectly no matter what. Okay. Now this isn't very good. That's too thin. In the interim, the Mathematica is so slow that you just have to sit and wait for it. Oh, that's really thin too. But let me make it a little thicker than that. Okay, here we go. But anyway, the code looks real simple, but it took a while to figure this out. So there again, we have two donuts, and again, independent of thickness of the donuts, they're going to fit together perfectly. Okay, but what I really want is three donuts, and I don't remember why I did this. Oh, what I did was, what omega is I'm playing with the thickness of the donuts without changing their orientation. So if I make the donuts a little thinner, that's what this is showing. Then so omega is, if omega is greater than psi, then the donuts are going to be too thin to touch. If omega is less than psi, then the donuts actually pass through each other. That's what this was showing. And only when omega exactly equals psi do they just touch. And that's the critical. You can clearly see that the donuts are now passing into each other because omega is less than psi. So that was just, I wanted to prove to myself that I was right, and I did with this. So that's why I did that. The next step was to be able to do three donuts to figure out where they are, and I did the same thing with omega. And it turns out, again, the point where they just touch is when they are the same thickness as the original donut. And when I make omega a little bigger, you'll see there's a little. I'll just make it a little bit bigger. You'll see a little bit of space between them. It takes a while for it to show. Oh, for crying out loud. Mathematica is really slow, or else my computer is really slow. But here we sit and wait. What I want you to see is now omega, which is controlling the thickness of the individual donuts without changing the thickness of the outer donut, is when omega is large, or maybe it's the other way around. Omega is controlling the thickness of the inner donut, and psi is changing the thickness of the outer donuts. And so when omega is greater than psi, the donuts aren't quite thick enough to touch. And believe it or not, it's still not done. But
Greg, this is Robert Kemp. What I was trying to explain to you before is that you're trying to run this math computer program over the internet, and it's using up random access memory resources.
Yeah,
And it's not only affecting your computer, it's even affecting mine. And I've heard others say the same thing.
Okay, can you see this now?
We can see it. It's just that it's moving slow because you're just
Okay, well, that took a long time to compile, and I won't do any more of that. But what I want you to see is that there is space between the rings now. Hopefully you can see that, and it's everywhere. So now that the rings are, when omega is larger than psi, they don't in touch. So my point is that the thickness of the ring, when there's 3, is exactly the thickness of the original ring. That's both for the case 2 and for 3. That was a surprise, but and which is another reason why 3 is special. Okay, but when we move into the outer rings, we obviously have to contract these rings, have to be made smaller so that there's room for the next 3 rings. And so that's what I'm going to. What I did here. Oh darn. Oh, here we go. Okay. All right. What this is, and hopefully you can see, is this is not 9 rings on the surface of a donut. This is 3 sets of 3 rings, which is different. So this is my second order model of what I'm envisioning. But when I tried to do the next level, which is 3 sets of 3 sets of 3 sets, it never got done. So I need somebody who can do computations like this. I need a way to figure out how to do this, and then I want to keep building this model, and I want to have more and more levels. But again, if we can get this structure built, then I can turn it either in the plane of the thing or in a different plane. I can get whatever knot I want. That's not the hard part. That's the easy part. The hard part is figuring out the structure within just one circle. I hope I've said that enough to convince at least somebody. And again, there has to be this shear, going back to this idea of shear modulus, and relating the shear modulus over the mass density, okay, is equal to the propagation speed squared, c squared. I believe that's what we've got to achieve. We've got to, in some sense, get a shear modulus. In other words, there's this shearing going on between all these things, so they're constantly. I guess what I think of is the scrambler. You've all been on that amusement park ride, the scrambler, where these different, you're shearing up against these other parts, and then you're shearing up against something else, and then in the process of the whole ride, you eventually come in contact with everything. You come closer to and further away from other things, and that's what I envision is this scrambler ride of a model that has a fractal structure to it, but everything is built out of simple circles. And it's the way the circles come together that create the topology, that give us the shear, that give us the stability. And again, all this could be in vain if what I end up with isn't stable, which is why I want to create tools. And that's why I wrote the paper that I did, mathematical tools to be able to test models for stability, because that's the ultimate test. Can I find a model that holds itself together, that is stable, that explains charge in terms of positive and negative, and then from there, hopefully, we can build a model of the neutron, and from there, hopefully, different models of the atom. We can ultimately, hopefully, explain why does positive charge track toward the nucleus and negative charge toward the shell. If we can do that, then, in my opinion, we'll understand why we have gravity. That's the ultimate goal, and that's where I'm heading for. So, but this is step one. I'm not even to first base yet, and so I have grandiose ideas about what could be done, but I got to start with just these basic ideas first. So I had a whole lot of other stuff I wanted to share, but we're coming up on 11 o'clock, so I'll go ahead and let's see if there's anything else in this file. This was the attempt at the 27, but it never compiled, and I got a whole bunch of other stuff I took out to avoid that. So I'll be done. I'll move back to my presentation and stop sharing the screen, and I am open for questions. If anybody would like to, you can unmute yourself, so just go ahead. You can raise a flag, or we can just take turns.
Good morning from Arizona, Greg.
Hey, Don.
Yesterday you showed us your tubing, and you twisted it to make the loops that corresponded to platonic solids at the intersection of a sphere and a torus. Is that the way you said it?
Yeah, last week you mean? Yeah. Last week it worked, but this week
Yes.
for some reason I couldn't get the cube to work because something.
Well, I have something I really need to share, and it's about the difference between Borromean whatever rings and your torus knots. You show in the first slide you showed your Sagnac award, and those are 3 separate rings, right?
Here it is, right here. Yeah, 3 separate rings.
The picture beside it on the right.
Just so everybody knows, they're actually towel bar rings. That's what they really are.
Oh, okay. And on the right of that, you have the one continuous. No, those are 3 separate rings also.
Yeah. I just wanted to show. This is another example. This is the same topology as the 3 rings. These
well,
rings
let's just imagine. Okay, imagine the one on the right is a torus knot, and it would be one continuous loop that goes through the whole. The torus knot has a relationship to the Borromean rings if you do what you did with your clear tubing, and that would be, let's take the large torus, the fat in the upper left.
Sure.
If you had a great big large torus cutter and snip that, like you're taking a bite out of a donut, you've cut it. Now, you've got a cut and a floppy donut, and you take your clear tubing you was playing with last week, and you hot glue it to the outer surface, right? So the ends are at your cut in the donut. Now, if you hold one side of that intersection fixed and you start to twist the other side of the intersection, you'll twist the tubing on the outer diameter of Villers on the major diameter. You'll twist your tubing up into a torus knot. When they come around and first meet, you'll have a 2-1 torus knot. Now, I want to draw in a reference to a patent, which then a reference to resonance, which draws in a resonance to nature, but to connect first to a torus knot in a bifiller circuit that comes to resonance. Instead of cutting a electrical current loop, which these shaped like these torus knots, instead, if we leave it as a solid loop and conduct from one point on the major diameter across both ways around the solid loop to the opposite side of that major diameter, we'll have what I'm reckoning, and I really want anyone to chip in on this, gently, the same thing as a torus knot used as a metamaterial to deflect radar waves because it is self-resonant with the radar frequency. It's made the right size for the radar frequency. They'll take mats of these torus knots, like a chainmail, and use those as a backing behind a radar antenna to keep from flooding the airport office with radar, for instance, or such. Right? Now, if that knot is self-resonant, it is going to be resonant by canceling its own self. It'll absorb some of the impinging radar to do that. But if it's self-resonant, it will essentially have created 2 node points on opposite sides of the outer major diameter that are neutral. Now, if we passed current through those neutral spots, we would reinforce that self-resonance. It would only be in effect during the rise and the fall of the current. But that knot, just like Marin Solyachek found, will have a self-resonant frequency to where its own magnetic field is the only thing oscillating. It will have 0 electromagnetic outer influence. You'll have a fixed, canceled magnetic field. So how do you turn that into a torus knot that's 3 times longer? You take and turn it 1/2 turn, and you have the same as the patent I want to reference, which is called a Mobius resistor. But what a Mobius resistor is the same thing as in your with a great big torus donut cutter. It takes a capacitive strip, just like you played with as a kid. You turn a strip of paper 1/2 turn and tape it back together, and you'll take a pencil around 2 times before you get back to your starting point. That's a Mobius strip. If you take a circle, twist it around the torus, and come back to itself, you make if you take a capacitor, it's 2 conductors and a dielectric between, and it's a strip, and you twist it, connect it back to itself. What you have then is a bifiller circuit that goes from opposite side to the other side of the piece of paper to complete itself. Now, what pulls the capacitive and the inductive together is, let's imagine this. Your conductor is 3 on the surface. If you twist it 1/2 time, if you have the bottom left NPA Sagnac award is 3 separate conductors. Let's take our great big rubber donut cutter and click that, intersect that chop it, grab it, do 1/2 twist.
Mm-hmm.
What will have created those 3 rings then all become one long ring 3 times as long.
Yeah. Okay.
Okay, now, the interesting thing is, in doing that, you line conductors up so that opposite sides of the donut has conductors opposite each other or in a triangular relationship. Excuse me, there's 3 corners then. Essentially, what I'm saying is the Mobius strip is a planar a cycloid object going through a torus surface.
Mm-hmm.
If you have a triangle and the cycloid of that triangle going through the torus makes a triangular surface that has an edge. In other words, the triangular Mobius cycloid has edges that are a 3-2 torus knot.
3-2 torus knot is a trefoil knot.
A 3-2 torus knot, yeah. Yeah, it is a trefoil. Now, the difference in the one you had pictured is a 2-3.
Yes, you're right, but ultimately, topologically, they're the same, and that's pretty interesting. That we probably should have a different name for a 3-2 than a.
I don't know quite what you mean by topologically the same.
I mean, if you were to take a piece
section, you'll have 3 wires going through it, but on the other, only 2.
If you were to take a piece of rope and actually follow that path,
right,
and then take away the donut,
right,
and then see what it does, it's the same knot. They're both the same knot.
Okay, well, we would need to.
In fact, MN. This is important. Okay, now let me clarify for people that aren't following what we're talking about. If you were to go, I'm looking at on my torus. Okay, here. There are so many things about toruses. I could just talk all day about toruses.
Yeah,
anyway, you could go around the torus 2 times around the cross section and 3 times around the whole thing, and you get one sort of formation. In fact, I could show this if you want me to take. I'm afraid to take the time because it's compiled slowly. Or you could do the other way around. You could go 2 times around the cross section and 3 times around the loop. And the question is, for a while, I thought they were 2 different knots, and that was a real surprise to me to find out that they are in fact the same knot. And so I did. I literally took a piece of rope and I tied it, so that it would follow that path in both ways. And I think whoa, I got some kind of an echo there from somebody. Anyway, and it turns out that they are, in fact, the same knot, and that is true for any M. So M times around the cross-section and N times around the loop is the same as the reverse. M times around the loop and N times around the cross-section.
Okay.
It's the same knot, although it looks different the way, because when there's more loops, then it looks kind of like it's going down the toilet bowl. That it looks kind of this way. When it's going more the other way, it looks more like a slinky. So, but the knot is the same, and so the key is the relationship between them. That's what's important.
Okay, great. And what I do want to point out, what I sort of want to leave with you is that nature apparently is doing by self-resonance when it's doing any kind of a toroidal instance. And to pull this in, if we had the great big rubber donut cutter, sliced it in half and twisted it, you're putting those half. For every half turn, you're going to another degree of torus knot, which is going to make another group of platonic solid points on your special spots.
Yeah,
right?
That's what I learned about Don Burdell's stuff, yeah.
Oh, cool. Now, then, if you consider that there is a second torsion at play, you were speaking of the in spiral and the out spiral that you can see when you have these circles spiraling into the center. And you were referring to those have an interaction amongst themselves.
Yeah, okay.
That pinch effect.
Right. This is can I make a point about pinch effect? This is really interesting. If you were to just have, let's say, a bunch of Villar-Sow circles on the surface of the knot, surface of a torus, looking at them from this point of view, let's say we didn't have just one, but we had, like 20. In fact, I've got pictures of it back here. Let's see if I can get to it. There's one with 35 of them. Okay. Here's one with 35. What I want you to notice is that it's denser towards the center than it is towards the outside. Everybody can see that, hopefully. Okay. Well, what's really it's really interesting. There's two things going on. There's a pinch effect, obviously, because they're coming closer together,
and they're going the same direction through the hole.
But yes, they are. But they're moving faster relative to their environment at that particular point, because the angle between them is is greater at that point. So the two things balance, and we get a really nice. I didn't say that quite the way I wanted to say it, but Faraday's effect. In other words, it's the tendency for it to want to pinch is balanced, which is the Amperian effect, is balanced by the Faraday effect of its moving with respect to its environment, wanting to twist. It's doing more twisting at that point too. So the two are balanced, and so that the net thing can continue to move at speed c. It doesn't actually speed up. It only is speeding up relative to its environment, based on the other parts of the things. Oh boy, I wish I could say that more clearly.
But thanks for the time to share what I did, and I could really. I love the way that we can connect. Go ahead.
Yeah, and I hope that we can, Don. I really do. Okay, anybody? I don't know if I explained that quite the way I want to, but it is absolutely amazing that it's both effects going on at the same time. They balance each other perfectly, so that the speed of the charge throughout the whole circuit is just c. It doesn't increase when they pinch, because there's also the Faraday effect going on right at that very moment that balances it. And that is what I'm looking for. And can I just say one last thing related to that? That is that the idea that what you were talking about, self-sustainability. What am I trying to think of here? That idea is exactly the point. The same thing. What did you call it? You had a different name.
Harmonic.
No.
Self-resonant.
Self-resonating. That's the key. That's exactly what we're looking for. We're looking for structures that are self-resonating.
With bifilar conduction.
Absolutely. And that's exactly what this is. The ultimate in self-resonating structures.
So you described one torus system by twisting up the big rubber donut that was cut, twisted around, so you have a torsional strain applied to the continuous torus loop, right? So it's storing then, if you reconnect it, it stores a torsional twist. If you cut a donut,
the torsion isn't in the path itself. It's in the relationship of all the stuff going on around it. That's what's creating the torsion.
Then there's a torsion
stuff
involved.
Doesn't move except in relation to other things. Remember?
But going around the torus, there is a torsion involved to get the twist in the beginning, in the first place. In other words, this is a twisted helix going around the torus.
You're just talking about the practical solution of...
No, in the fact that there is a spin going on, implying there's a torsion there if it's held at resonance.
Well, again, I'm not asking the question what made it start in the first place. I mean, that's a...
Okay, but what I'm saying is there's a torsion.
I mean, God did that, you know. But now it is moving, and what keeps it moving? That's all I'm concerned with.
Well, I'm just trying to point out you have two sources of torsion you're talking about. One is around the torus, and the other is through the axis by the conjugal spirals going in and out. Those two mechanisms will interlock, and the axis spirals, Greg, those if all of the density of the magnetic field can't get through the hole the way it does on the outside, that torsion could come to a valence place and could go stable. So what I'm saying is there's a chance to get stability of torsion lock against torsion lock. And I'll leave it with that because I'm at the edge of my known brain matter. Thank you.
Yeah. Very good. No, I like that. Thank you. You made a lot of comments, and I wanted to... I've lost almost all of them now. There were so many. But anyway, I'll open it up to other questions if anybody has any or comments. No? Okay. Somebody? Oh, Sean Torbedal. Go ahead, Sean. All right. Sean, you need to unmute yourself, Sean. Can you do that? There.
When you talk about C and you're talking about the speed or something C in there, are you talking about the speed of light?
I am, but see, as I tried to say early on in my talk, I don't like to call it the speed of light. I don't think there is a thing called light that moves at a speed that we call the speed of light. I just don't think there is. I view light as an interaction. It's just in the same way, and I've said this many times, and I see Professor Keene coming up, so I'm well aware of the fact that rotation is an absolute thing by virtue of shear, but nonetheless, I like to say that light is a measure of relative rotation, just in the same way that heat is a measure of relative translation. So what's moving at C is the stuff inside, and I want to call it charge, but I want to be careful there too, because I don't mean positive charge or negative charge. I mean primal charge, that stuff that moves. So whatever is moving, it's moving at C, and it's moving at C because that's the speed at which, if you will, the shear velocity, the shear modulus equals the bulk modulus, or whatever, the mass density. So that's how I'm seeing it. The stuff has to move, or it won't be held together, and it has to move relative to other things in the same system. Does that answer your question?
Yeah. Okay, so are you visualizing each one of these closed loops as a pathway that's, you're not thinking that the loops themselves exist so much as something moving in that path?
Right, they're a pathway, exactly. In fact, well, here's one way to think of it, the way I see it anyway. I see planets moving around the sun. We understand that they move in ellipse around the sun. But if you were to instead spread the planet out throughout the entire pathway of that the Earth follows, then every one of those elements would continue to move just like it is now. It just would be smoothed out, and each element would be replaced by an element just like it behind it, and we would look at that and say, hey, it's not moving. You see what I'm saying?
Yeah. Now,
that's how I see it.
When you were talking about shrinkage, like let's say you took one of these geometrical paths of closed loops, and you said that it would shrink and then it would change some properties of that particle or that system. What did you
I don't
mean?
remember using the word shrink, so I'm not sure. Are you talking about it gets more condensed toward the center? Is that what you mean? Okay.
That's what I mean.
All right. Well, what I'm saying is, again, the Amperian principle, the translation principle, says that when things get closer together, just like when you put your finger over the nozzle of a hose, things have to move faster. But at the same time, the Faraday effect says that when things are shearing more, then they're rotating more. So that's what's causing the twisting. So just at the same time that the Amperian effect is coming into play, making it pinch, the Faraday effect is causing it to spread out, and so it continues to travel at the same speed. I really would like to come up with a better way to say that, but I'm still working on it. But that is what's going on. I can show you the math, but I'm trying to make that clear in my own mind so I can make that statement with some conviction. So anyway.
So what is the mechanism shearing? I mean, if there's two systems that are moving through these loops.
If you think of these loops as again a continuum of charge or something flowing through them, they're obviously more condensed toward the center. So you can think of it in terms of capacitance and inductance, if you like. When the stuff that's in the center has more capacitance, more potential to move away, more to spread out, more storage of charge, whereas the stuff towards the outside has more inductance. And it's just as it moves through the circuit, it's going to go through both. It's going to do that ebb and flow, and yet throughout the whole process, it just stays in a circle. Does that help you?
Yeah, thanks.
Okay. All right. Let's see. Pal, were you next? I don't know. Why don't you go ahead?
I think Robert Kemp was next.
Okay. Robert, you
go ahead, Pal. You can go ahead.
All right, Pal, you go ahead. Then we'll let Robert be next.
Okay. My question is, what happens in a torus, or even a simple sphere for that matter, if the center and the surface gradually trade places? In other words, the center begins to expand to become the surface of the sphere, and the sphere surface begins to contract until they have traded places.
Sure. Yeah. I mean, I believe, that everything is about motion. So right. Every element in this circuit that I was just doing just that. It's it's expanding relative to its. Again, you have to understand that expansion is something, and I didn't say this, but expansion is not something that an element by itself does. Expansion is something that an element does relative to the other elements, right? An infinitesimal thing can't expand and it can't rotate. Rotation and expansion both are group phenomena. Things are rotating relative to other things, and they expand relative to other things. They can translate on their own, but you understand, just logically speaking. So as what's going on here is, as these circuits are moving away from the center, they're expanding, and then in expanding, they're creating more. They're getting more inductance. They're turning more relative to their environment, and then in the process of doing that, that induces the contraction, which is the Ampere. So the Amperian law is inducing the contraction. That's the pinch shift, and the induction is inducing the expansion. So we get this whole cycle, and it's just natural. We see it in sine waves, electrodynamics, everywhere. We see this natural process, expansion and contraction, and the process as a whole is stable. But any given element in the process is going to be at different cycles throughout the process. Does that get you where you want to go?
Yes, indeed. Just further, clarification. Do I understand correctly then that this process will still maintain the integrity of the different shapes that you showed, dodecahedron and cubes?
Well, okay.
And
sure. Yeah. Here we go. Here's the idea. If I can find a structure that's stable and that has satisfies all the equations, which we could characterize in terms of Maxwell's equations. If it does that, and stability by definition, as I said at the beginning, means that the energy is minimal. And any change in the structure would increase the energy. So if we can find a structure that does that and yet is dynamic, the dynamics are necessary or it wouldn't hold itself together. So we have to find this dynamic ebb and flow sort of structure, and the whole thing as a system is stable. Then I can take that system and add it together mathematically with another system, which is also based on a circle, which is also stable, and then just add them all together vectorially. And I believe then the overall structure would then have properties that we could at least understand. I'm not saying it necessarily would be stable, but that's where I'm going with this. Is what happens once I've got the circle? Then how do I add that with other circles vectorially to get what other structure I want, and can I achieve stability in more complex ways? And I'm sure that we can, because obviously we have atoms and things. So
yes,
that's where I'm going with it.
Yeah, that's very good. It's very helpful.
Well, I will say this. Now, you have to remember, and I said this before, talking about my entropy idea, you cannot add energy, and this is where I believe one of the, and I love David Bergman, so I think he's great, but he begins by doing the integral first. He begins with inductance and capacitances and then the geometry. I'm trying to begin with the elements themselves and then adding them together. And because once you add together finite things that you've already integrated, then you have the problem of you might have missed some interactions. Okay, because the whole is different than the sum of the parts. So if you've already integrated, you've got the whole already, and you can't look at the way the sum of the parts come together. So I'm focusing on the sum of the parts. And again, another way to understand it is when you're dealing with fields, you can add them up. The field of A and B is just A plus B. But the energy of A and B is A plus B squared, which gives you A squared plus B squared plus 2AB. The 2AB is the mutual interaction energy, if you will, that doesn't have anything to do with A separately, A squared, or B separately. And you can't get rid of it. The only way to deal with it properly is to deal with the fields, if you will. So take my structure, add up all the fields of these structures, then calculate the energy of the whole thing, and see if that energy would be different than if I took the structures separately before adding them together, and chances are they would be. And the ratio of those two energies, that is the ratio of the energy of the whole system versus the energy of the system, the components taken separately, is, by my definition, the entropy of the system times Boltzmann's constant. So I don't know if that was that was a little bit of a tangent, but that's kind of where I'm thinking. That's where this whole entropy thing comes back into play.
You see, normally Harry Ricker raises his flag and tries to give you some constructive criticism.
Yeah, well, I'm waiting for that.
So I thought maybe I will make a small constructive criticism since he's not raising his flag. And that is, it seems to me that you seem to be biting more than you can chew. Like my eyes are bigger than my stomach.
Tell me about it. Yeah, well, that's probably true, pal. I've been working on this for a long time, and it's a hard problem. I won't say I've been working on it consistently. Like I say, it's easy for 6 months to go by, and I get busy with other things. I get interested in other things, and then, so I must have 50 projects that are half done, that all related in different ways. I know Michael Evans was here, and actually I was planning on spending some time talking about some of his stuff because that relates indirectly with some of these things too. But
yes.
So yeah, well, thanks, pal.
Thank you, Greg.
I don't know who's next, Professor Keene or Robert Kemp. Who you guys decide? Doesn't matter. Professor Keene, let you go. Robert already had a chance, so I'll let you go next.
Am I next?
Yeah, you go next.
All right. Several things, Greg. First of all, I'm going to tackle responses to your points that you're trying to make in things that might be allied to giving you some answers. First, fixed points versus non-fixed points. Now, people know that if you have translation types of things, there are no fixed points. And this is one of the topics that are different from dealing with motions that involve fixed points. And fixed points always are related to rotations and of some sort or another. And
there's fixed points are or not related to rotations?
Are. Fixed points are. The fixed points are related to two things. One, they are related to H over M possibilities, which means viscosity.
Mm-hmm.
Kinematic viscosity is literally H, Planck's constant, divided by a mass. And so you can put this into your equations and look at it as if it was an electromagnetic system rather than H over E, which is what you do to develop electromagnetism.
Okay.
Next. The thing is that from my point of view, I've learned that I must understand anti-symmetries. And almost everything that you're supposed to do where you're trying to do something geometry-wise, you are dealing with symmetries. Stress energy symmetry, group actions which always have a symmetry associated with them. Well, you don't have to do that, and to me, it's preferable to try to look at the anti-symmetries. What's the best example of anti-symmetries? It's the matrix of EM intensities that you can deal with. Okay? And people are familiar with that. Whenever you can write down a Pfaffian form or a equation called a one form of action, if you will,
Yep. I remember your 1, 2, and 5, the 4 forms. I remember that. I'm definitely planning to use that.
No, but it is, because when you put in 3 rings, you're dealing with a Pfaff dimension 3 problem, which has some stabilities if you will tag along spinors.
Okay.
Zero eigenvalue that will always be related to the 3 entries. And I was going to suggest to you, have you tried putting in 5 instead of 4 rings? Because the 5 rings would be non-stable in a topological sense. The 4 state in a topological sense is not stable, but the 5th one could be a stability just like the 3 is a stability.
That's a possibility. Yeah, I'm open to that. I'm open to trying different things. Again, my idea was to build a fractal structure off of 3. So 3 of 3, each of having 3, and so on. So it would go 3, 9, 27, 81.
Yeah, but you can now. It goes to the last point. the way that you talk about evolution when you're dealing with anti-symmetries is to use the notions developed by Elie Cartan in 1923, as a matter of fact, in that era, where he developed equations of motion by looking at anti-symmetries. And this led to a concept, because he had studied with Sophus Lee and all the rest of these guys, to use Lee's exterior differential as the propagator, as people doing geometry, the covariant derivative. They're two distinct different things, but if you use the homotopy, as it's called in the literature, this will define a operation of evolution. That homotopy can be transformed into exactly the first law of thermodynamics, which does not require symmetries. This can be worked on anti-symmetries alone, and that's something where you might pay attention to it in what you're trying to express here. Get rid of the geometry. Get rid of the geometry. Or if you're going to use geometry, you're going to have oddness in the fourth dimension thing. If you're going to have non-stability, you're going to have fourth dimension 4, and you could go as Ferris Williams has done to 5 dimensions to get back to a stable system. Does some clever things here.
I'm a big fan of his. I've been reading his work. Yeah. So I like Ferris's work a lot.
Well,
I don't know. It's hard for me to say get rid of the geometry. I guess I like to think of this as dynamic geometry. In other words, it's not, again, just like that I was explaining. The quantum change comes from the fact that a structure can be altered dynamically. So we have two different frequencies: the frequency of the rotation of the object and the internal frequency of the object. When those make quantized changes, we see quantum events, which we call photons and so on. I believe that's really important, and so it isn't just static geometry. It's the fact that these things are moving that makes for that thing. So I like to call it dynamic geometry. I don't know. So you think I should get rid of dynamic geometry too?
I think you want to get rid of geometry in your thinking. Then you'll do better in being able to analyze these really tough problems that you have here.
Geometry is about all I think about, so that would be a big change for me.
No. If you think about electromagnetic fields and the antisymmetric configuration of those matrices, you're thinking about topology and antisymmetry.
Yeah. I understand. I appreciate that, and believe me, I am. I've mentioned this before. This idea of doing this Fourier breakdown, in my opinion, one of the applications, and I haven't pursued it, but I want to, is a new development of knot theory. Because if you think about it, if I've got a closed path, however complex it is, it's going to form some sort of a knot, or reversing that, every knot is going to have some kind of a path. And
but let's make your knot in 3 dimensions, and let's make your knot in 4 dimensions, and let's make your knot.
I don't care how many dimensions you make; it doesn't matter. The point is I can break it down into its Fourier components, and each of those Fourier components is an unknot. So what I have is a bunch of Fourier components that are related to each other in a certain way, and the relationship between those unknots creates a knot that somehow is in the information of how those components relate to each other, and that is fascinating to me. I just haven't been able to pursue it, but I think it would be interesting.
Well, for example, to this particular point here, if you take 3 strands, you can form a braid. Okay.
Yep.
And if you close the strands back and forth, you've got a knot.
Yep.
Now, but if you take and rewind the system in another way, it is possible to create what is called the unknot.
I know what the unknot is.
Okay. Well, one of them, they're both from these trying to represent things in terms of threads, and when you have to define things in terms of thicknesses, I think you add more to the problem, and that I think you want to tackle those problems via anisymmetry.
Yeah, it's the structure of the thickness that I'm most interested in. That's my number one problem, because no matter what I'm dealing with, if it's finite, it's got to have structure along the path. And then I want to know what that is.
Fine, but that may not be geometry that you're dealing with. It may be topology.
Very possibly, but again, going back to this model I was talking about, what topologically, I could sit and figure out. Okay, I've got 3 rings, and they're going inside 3 other rings. This 3 rings of 3 is different than 9 rings. Okay, I hope I've made that clear. And so there's going to be difference topologically in terms of group theory, in terms of lots of different ways of looking at it. And so maybe there's ways of combining these rings that would correspond to the different sorts of groups. I've thought about that. So that somehow, again, I'm looking for something that's fractal, but somehow maybe a particular, like I said, 3 groups of 3 forms a different group than 1 group of 9. You know that.
Yeah,
and
but I like your discussion on 2 and 3 knots versus 3 and 2 knots because they are homeomorphically equivalent.
That's right.
That is, you can cut these things and put them back together by gluing processes.
Yeah.
And that's a topological change, but it's not a continuous topological change. And
I got it.
The homotopia concepts put in that you can make changes in topology which are continuous.
Yeah.
Apart.
But see, what I've been pleading and thumping my fist about is that even discontinuities can be explained by the interactions of continuous changes in 3 dimensions. We need 3 dimensions to. That's what I just said. Okay, that's the strobe effect. You've got your wheel turning and you've got your light flashing on and off. And if the flashing of the light is in sync with when it moves forward, it looks like it's holding still, but then it slowly moves back forward. Bang! Oh, we get this change. It's a discontinuous change due to a change in 2 continuous things, and that I believe is fundamental. That's my whole point. Is, in other words, that's what's going on when I've got my little model that I was explaining earlier, which I think is the next slide. Okay, right down here. These Christmas tree lights are firing off and on in a circle, but at the same time, so that's going to have a frequency, and at the same time, this whole table is spinning around in another frequency. So you're going to see these these circles are going to appear on the surface of a donut, which has the radius of those circles. And depending on the speed of the spin of the table in comparison with the speed of the frequency of the Christmas tree lights turning on and off, you're going to get different quantized states. And by changing, alternately changing the frequency of one, you can get discontinuities in the interaction between them. Another example is a bugle. You blow on a bugle. The energy that you put in, there's a continuum of energy, but you're going to get a discontinuity because you're only going to get, the fundamental, the fifth, the octave above, and the third. You're going to get quantized changes in state because it has to do with the geometry of the bugle. And I'm saying that's exactly what's going on with the particle. The geometry of the particle is such that it's got its own internal rotations, and when you rotate the whole particle as a whole, then that frequency is interacting with the internal frequency, and if those frequencies become sufficiently high, it can actually change the state of the particle. And I'm saying that's what a photon is. There's no such thing as a photon or a muon or whatever the heck they are. There's no such thing as a bugleon. It's just a change in state due to a continuum of change in the energy input. So that's my argument.
To me, the speed of light is not a continuous wavy type thing. It is a propagating discontinuity.
Right.
Sure, I'll go along with that.
It's an extremal solution to the wave equation, which is linear, but the equation that you have to solve is a nonlinear equation, a quadratic form, and
Sure, I buy that.
Okay, but it's a discontinuity, and when you take the moving wheel and you're comparing the speed associated with a propagating discontinuity with the speed that is actually mechanical and visible as a geometry type effect.
Mm-hmm.
And
Well, I guess maybe we're going to disagree on this, but in my mind, there is something that's actually moving, and it moves at speed c relative to its environment. And
yes, that's the optical signal. That's the optical signal that catches your eye.
Right.
Well, okay, but I think that there is that. Okay, let me back up. My very first fundamental principle, my number one assumption before I start anywhere, is that matter exists. Something really, truly does exist. There's something that's real out there, and whatever that is, I call it matter. And I've been through this argument before. So by definition, matter is the stuff that exists. And I spent a lot of time going through this argument, saying that whatever matter is, it has to have certain properties, and it's going to repel other matter, and it has to move in order to be able to condense with other matter in obeying of Ampere's law or Ampere's principle. And through a long series of arguments, which I've made in lots of other presentations before, I come to the conclusion that whatever matter is, it behaves an awful lot like charge, but not charge that has positive or negative value, but I guess what I would think of as a primal charge. I didn't just invent this idea. I deduced this idea from the assumption that something exists, and it isn't energy. Energy is the relationship between things. Matter is the thing itself, and the matter itself has to move. What
we're questioning is your concept of a photon. You're saying that a light is not a thing, and I'm hearing
light is energy. Light is energy. Energy is relationship.
But what Keen is saying to you is that that is discreteness, that represents quantization, that represents discontinuity, but you are somehow contradicting yourself. That really is what's happening, because you're saying it's not and it is. And that's why we're asking
what I'm saying is the interaction. No, I don't believe I'm contradicting myself, but let me try to say it again. What I'm saying is that the interaction of continuous frequencies is responsible for any and actually all. I'm going to claim all discontinuities that we see in Lissajous shapes, in the wagon wheel, of the movie that moves backwards, the strobe effect, this model that I built, the quantization of redshift. I believe it has something to do with the fact that the universe is finite, and yet there's these changes, there's these circuits or whatever that are happening that are causing quantization of redshift, known by Tift. I believe all quantization ultimately is a result of the interaction of frequencies. Everything, I need someone to give me a counterexample, because everything that I can find.
The counterexample is what falls into your eye.
Photons. What's going on there? Here's
what
what's
is
going
a photon that's falling into your eye? Is it discrete frequencies or continuous frequencies?
Well, we could think of it. I mean, if you want to think of the electromagnetic field, we could. I'll be okay with the idea that a photon is a node. It's a particular kind of discontinuity in the electromagnetic field. I'm okay with that. So in that sense, yes, I agree. There are discontinuities. But what's really going on, what the real matter is going on, is that there's circulation in this circuit, but there's also circulation in some other direction, the cross section, throughout the cross section of the circuit. And for whatever reason, the atoms in your eye are rotating in such a way that they're caused to rotate in such a way by the advent of this light, or the other things that are causing the light. Really, the relative rotation is such that your eye is perceiving. Your eye is actually changing state because of the rotation of the other of the things.
There's nothing in optometry or ophthalmology that shows that.
Each time they change. Just like this thing is changing state.
A cone or a rod into your eye of a particular frequency.
But your eye is made up of atoms. It's made up of particles. And the particles is what I'm talking about. The particles themselves are actually changing state. They're actually doing what this model is doing. They're actually, there's this internal spinning, kind of like the Christmas tree lights, but the tabletop, that is, again, how much it's rotating is relative to other things, and it's actually rotating more or less depending on how all these other things, which we call light, are being sent to us. But it's a measure of energy. Energy is a measure of relationship between things. It's not a thing in itself. And that is really hard for a lot of people to understand or accept. But that's
because
I'm sticking on it like this.
It sounds contradictory what you're saying.
No, it's not at all. How do we know that a ball has potential energy when it sits on top of a hill? It's because of the hill. If the Earth wasn't there, it wouldn't have that energy. How do we know that it has kinetic energy? Because it's moving with respect to the Earth. So what I'm saying is its energy is whether it's kinetic or potential, is by virtue of its relationship with the Earth. Okay. Likewise, heat. How do we know what is heat? We used to think there was a thing called caloric that actually moved from a hot body to a cold body. Now today we say that's how silly can they be? It's not that. It's just in the hot body, the little billiard balls are moving around, translating faster with respect to each other than they are in the cold body. And that motion, the relationship gets transferred from the hot body to the cold body. And I'm saying light is exactly the same. Light is just like heat. It's not relative translation, it's relative rotation, because these bodies are not little billiard balls. They're not little dots. They're dynamic systems that are moving. They have to move in some sort of complex circuit. I don't know the details of the complexity, but I know that it's got to be some kind of a circuit. And that circuit is demanding things like spin and angular momentum, and it's demanding things. Those are important, and that is the source of light. It is the relative rotation of these particles that is actually what light is. And light is not a thing that transfers through space. We can account for it that way, but that's not what it really is. Just like we can account for heat, we could say heat is caloric and account for it that way, and it'd be all right.
That's where the contradiction is. If we can account for it that way, but then you say it not really is, I'm okay with you saying that's your own personal theory.
No. Well, the problem is when we start accounting for it that way, we run into all the problems that we know having to do with Einstein, where we treat light as a thing. Here's Einstein's.
No, we measure light. We measure light all upon surfaces.
I know, but we want to understand what light is. What we're really measuring is the matter. Okay, the measuring device is made of matter. So there's stuff in the measuring device that's rotating in a certain way in response to what's sent to it. The stuff that when you say that there's actually a beam there that travels from the source to the receiver, you're inferring that, because all you really know is what's going on in your eye and what's going on with the measurement tool. The rest is inferred. Okay, and what I'm saying is,
true. And the reason I would use Doppler as an effect, but the Doppler that we hear is because of sound waves, and sound waves have an attenuation. But in this ether or where light propagates, that may not be the same instant.
Well, see, what you're doing is you're creating a second kind of matter. I'm saying there's only matter and there isn't anything else, and you're saying, well, there's matter, but there's also ether, because otherwise light wouldn't have anything to propagate through. I'm saying no, there's only matter. That's it. That's all there is. And it's the relative rotation of matter, and we call that light. We can account for it by fields, and that's a great thing to do, and we should do it. But there's really only matter. That's my fundamental starting point. There isn't matter and another sort of matter called ether. No, there's just matter.
Okay. So what's going to happen when we prove that to be different? Are you going to change it?
You'll never prove it, because you'll never measure anything except with matter.
They're actually claiming
you'll never be able to. No,
they're
Robert.
actually claiming that the boson.
You're not hearing what I'm saying. You're not hearing what I'm saying. No matter what you measure, no matter how you measure it, you're going to measure it with an object. An object will be made of matter.
Yes.
Okay. So anything that is not made of matter is inferred. No matter what you do, there's no way around it, because you're going to have to use matter to measure it.
There's different forms of matter. Are you okay with that?
Sure.
Okay. Then now that is the case, because there's some matter that's called heat radiation, which they call matter.
Heat radiation is not matter. Heat is energy. You're confusing energy with matter. I'd make them distinct. They're not the same thing.
Energy, matter. That's how Einstein equals mc squared. He calls that form of energy equivalent to matter. Okay, now maybe that's...
Yeah, see, that's the problem. That's the number. That is the huge problem right there. Energy is not matter. Matter is not energy. Listen, if you have matter, then you must have relationships between matter. If you have relationships, there must be something to relate. So you can't have matter without relationships, and you can't have relationships without matter. Okay? So when you have one, you have the other. But they're not the same thing. Okay? So you can't have matter without energy. You can't have energy without matter. But they're not the same. And that's, in my view, that's the root cause of most of the confusion today, is confusing energy and treating light as if it were a thing, treating heat as if it were a thing, treating energy as if it were a thing. It's not. It's a relationship between things. And once we get that straight, then a lot of the scales come down. All sorts of stuff starts to make sense. Let me talk about Einstein, if I may, for a minute. Einstein in special relativity has two assumptions. He says, number one, the speed of light is constant in all reference frames. And I agree with that. Problem is, I don't agree that the speed of light is a thing. There isn't a thing called light that moves at a speed. What's moving at a speed is matter within these systems that we call particles. And they are moving at that same speed no matter how you look at them. So I agree with him. I just disagree with the idea that the speed of light is, that's the problem. We think of light as a thing. The second thing is he says that the laws of physics are the same in all reference frames, and all inertial reference frames. And I agree with that as well. It's just that there are no such things as inertial reference frames, because everything ultimately is rotating or involved in some sort of an orbit or a circuit. And that includes the planets, that includes solar systems, it includes everything. There's that when you clear those two things up, then I accept Einstein's postulates, and I can move forward. And all the math works just great. Everything works just great. But what we have to do first is separate the idea that matter and energy are the same thing, or can possibly be the same thing. No matter how I think of it, I just come up with nonsense. Sorry, but that's just, I can't. It doesn't work. So, okay. All right. Whoops. Is everybody frozen? All of a sudden, I'm not hearing anybody.
No, I was waiting on Keen. I thought he had more questions.
Okay. Well, listen, we're 45 minutes over time. I'm happy to take more time, but I will probably need to wrap it up here, unless somebody has something urgent they need to say.
Yeah, how about your neutron model? I have a question regarding your neutron model.
Well, this isn't mine. It's David Bergman's, but okay.
Now, you are accepting that as a model. Now, that's typically known as a hydrogen one model or a positronium model.
Well, hang on. Okay, let me be real clear on this. This is not the Yeah, I understand, but this is not the what we would call the free proton or the free electron. These are the bound proton and the bound electron.
Right, protonium.
The free electron is much larger, and the free proton is much smaller. Okay, and this is again just a first order model. So, like I said, it's not perfect, but it does an amazing job of calculating the anomalous magnetic moment of the neutron, which, as far as I know, nobody has done. Most people aren't even aware of it, but there is an anomalous magnetic moment. But you're calling this
the model of the neutron. This is your model.
Yeah. This is Bergman's model, and it's and again
the electron. You're promoting. This is a model that you.
It's a first order model. I don't say that this is the be all and end all. Again, it's a one dimensional model, because this charge is, he's not taking into account any of he's not answering the question, why is the electron negative and the proton positive? He doesn't answer that. He isn't answering the question, is there some structure along the paths? He isn't answering that. But he did answer one question, and it's very significant, and that is by allowing these rings to expand and contract and reach a new equilibrium, he can form a new thing. This neutron isn't really either the electron or the proton by themselves. It is a new thing which has energy, a mutual energy, due to the fact that they're working together. And that mutual energy turns out to be less, actually decrease the energy of the system.
Yeah, but there's nothing here that is about a neutron. If I add the mass of this proton plus this electron, I do not get a neutron. So how you can call that a neutron is beyond my understanding.
Okay, well, as I said,
the reason why you're calling it a neutron is because you have positive and negative, and you're getting a neutral result
No, there's way more to it than that. Way more to it than
and
that.
then that something you're calling a neutron.
No.
In physics,
hang on. Okay, what?
In mainstream physics, because you can call this dissidence physics. In mainstream, which is accepted in textbooks and everywhere, this is called the positronium, or this is called the hydrogen 1 model. This is nothing of a neutron. This is called false advertising. It's called bait and switch, because there's nothing here to tell you this is a neutron besides the fact that it's neutral.
Okay. There is way more to this model than you're appreciating, okay? Let me just explain. First of all, we know it's a neutron if it has the known properties of a neutron. What are the known properties?
The mass.
Which are, the mass is only one, the magnetic moment is another, the charge.
Which is the same as a proton and an electron and a neutron. They all have the same, so there's nothing different.
The charge and the spin, and I'm forgetting now, it has to have all of those properties. So if we can create a model that has that we can, basically take an electron and a proton and let them go, as it were, and let them find an equilibrium, which is exactly what we did. Okay, and the reason it hasn't been published or shared, I signed a non-disclosure agreement on this, so I can't disclose the details of it. But it's very complicated process, and basically what we do is the way he does it is I did it slightly differently. I reworked it, but basically he calculated the inductance and the capacitance of each of those. From that, he calculated the total energy, the mutual energy, added them together, and then made a change. It made them smaller or larger, and both separately, until both of them reached a point of stability. Okay, and it's a very, very involved calculation, but that's basically the model. And then, lo and behold, when he did that, he didn't start a priori with the mass of the neutron. He obtained the energy, or the mass, divide the energy by c squared. He obtained the mass of the neutron from this process. It just came out exactly the same, and the magnetic moment came out. Now I'm sorry, but I challenge anybody to come up with a model that does that.
But here's what I want to say, because there is something good here that you have identified. I don't agree that this is a neutron. If you use the regular, mainstream ideology that this is what we have named a positronium or a hydrogen 1, you can still, what you identified that is new is that you're calling this a capacitor. Now, it is not stated
it has capacitance because there's charge.
And that an atom as a capacitor. Now, modeling an atom as a capacitor is a new thing. It is a thing that could be done because this is something that can be
completely.
And you're saying that because you're saying it has the capacitance
and by virtue of the way the charge is positioned with itself, it has capacitance. These calculations were made 100 years ago. In fact, the books I can show you was a guy named Gray, who worked closely with Lord Kelvin, did a lot of took different geometries and calculated the capacitance of these different situations. Another guy is William Smythe in the 1920s and 1930s. These have been known for a long time.
Yeah, but not with our modern understanding of the atom. I
don't care how modern or whatever. These are the textbooks that Bergman uses. It's well-known stuff. If you have a system of charge, you can calculate the capacitance and the inductance by how it moves and how it stores charge. These are well-known things.
Yes.
Okay.
Now that's a great model to model the atom like that, but that's not a neutron.
That's fine. Listen, the goal of a model is to be able to recreate the known characteristics of what it is you're trying to model, and this is the most successful model I've seen to do that, because by allowing it to find its own lowest point of potential, find the bottom of the hill, lo and behold, it ends up having exactly the mass and magnetic moment known for the neutron, starting with just a free electron and a free proton. That, in my mind, is absolutely amazing. But, go ahead, find something better. That's fine with me.
That's it. Thank you. No,
Okay.
Greg, this is a great presentation. One of the things my last comment is that Powell brought up that you were taking on a lot of things.
Oh, yeah, I know.
What I would say, the reason it would appear that you're taking on a lot of things is that you're taking on physics which means you're trying to describe the physics as what's happening, and you're combining that with the geometry of topology.
Yep, all that stuff comes together.
Yeah, and that's so.
It's tough. It's tough, and the problem is I don't know where the answers are going to come from. So I'm trying all the answers. I do believe, and I agree that Professor Keen's work is really important, and especially some of the stuff he talked about last week. And topology is important, and knot theory is important. All these things are important, and so I don't have a book to tell me, where I should go. So I just fumble around and try to do the best I can with what I know. So, like I said, I'm looking for people who have a mathematical bent, who really kind of get the picture of where I'm trying to do, and help me. I think there's potentially some really good stuff. But all right, we're almost an hour over. I did promise. Who's meeting next week? Is it Peter? Peter, are you still here? So I will. Let me first close out the meeting. So we'll see all of you next week. Peter Kohut is going to be presenting next week, and I want to give him a chance to practice using the system now. So the meeting is officially over, but I'm going to stay here for a little bit. So